laureates, Professor Shuji Nakamura, Professor Anne Hager, Professor Fraser Stott, have kindly allowed us to use their name to for the awards. And so I'm also happy to say Professor Shuji Nakamura and Professor Fraser Stott, as well as Professor Kostya Novoselov are all present here today to help us to honor our awardees. So I'll hand the awards host, the program to our award host, Professor Paul West. My colleague, Professor Paul West, and editor-in-chief of ACS Nano. Paul?
I think Paul dropped his signal might not be as great.
Yeah. Actually, I'm here. If you can you hear me?
Oh, it's here.
Yeah.
Great.
Very good. I'm actually going to have to hand back to you, Professor Duan. In our rearrangements this morning, I didn't realize I had some things scheduled. So let me maybe show the slides for this first part, and then I'll come back for the second part as we described. Sorry for the scramble here, but maybe I can put up this slide for you and let you start with the introductions.
Okay. So should I take over?
Yes, please. Yes.
Okay. So I guess I'll start with the Nakamura award. So Professor Shuji Nakamura, the Nobel laureate in physics in 2014, invented a blue LED that has enabled energy efficient light source for many technologies, including solid-state lighting and new types of display. His invention certainly represents a perfect example of how fundamental advances in functional materials could transform our everyday life. So the AAAFM-Awards Award recognizes exceptional scientists who have made breakthrough advances not only in fundamental science, but also in technology development. The first Nakamura Award was awarded in 2019 to Professor Chad Moken and Professor John Rogers of Northwestern University, two pioneers in functional materials from both fundamental science and emerging technology point of view. Continue this tradition, this year we are honoring another two pioneers of the field with the same attributes. So it is unfortunate that we cannot physically present the award in person to honor our awardees. Professor Shuji Nakamura actually himself is here to help us announce and introduce our awardees this year. Shuji? Is Shuji on? Yeah.
Yeah, I want to open my Word file. How can I open?
You have the Word document in you?
Yeah, but Word file. I have to open Word file now.
Right.
How can
you want to share the screen?
Share the screen?
No, you don't have to.
No, just I want to open the Word file. How?
Okay.
Oh, how? I don't know. Oh, I don't know. How to open that? Okay, I got it. Okay, it's okay? Hello?
Yeah.
Okay. Okay, so Professor Steve Denvers is awarded the AAAFM Nakamura Award for his pioneering work in developing non-polar and semi-polar gallium nitride materials for energy-efficient lighting, micro-LED displays, and non-polar and semi-polar laser diode. Dr. Steve Denvers is a professor of materials and co-director of the Solid-State Lighting Energy Electronic Center, SLEEC, at the University of California, Santa Barbara. He obtained a PhD in electrical engineering from the University of Southern California in '88, MS Material Science in '86, and BS in Materials and Meteorological Engineering from the University of Arizona, '84. He obtained a PhD in electrical engineering from the University of Southern California in '88, MS Material Science in '86, and BS in Materials and Meteorological Engineering from the University of Arizona, '84. He obtained a PhD in electrical engineering from the University of Southern California in '88, MS Material Science in '86, and BS in Materials and Meteorological Engineering from the University of Arizona, '84. Dr. Denver started his 30 years career in semiconductors at Hewlett-Packard in '88 and joined UCSB in '91. In 2005, he was appointed the Mitsubishi Chemical Chair in solid-state lighting and displays. Professor Denver has been very active in entrepreneurship, having helped co-founded several startup companies in the field of photonics and electronics, such as Nitrous in '96, Solar in 2008, SLD Laser in 2013. He received the IEEE Fellow Award in 2005, the IEEE Photonics Society Aaron Kressel Award in 2010, elected member of the National Academy of Engineers 2012, Fellow of National Academy of Inventors in 2014, Spirit of Innovation Award from Pacific Coast Business Times 2021, and Quantum Device Award from ISCS 2021. He has authored or co-authored over 1,080 technical publications, 450 conference presentations, and over 185 patents. He is a highly cited researcher with an H-index of 140 and over 85,000 citations. Professor Omar Yagi is awarded the AAAFM Nakamura Award for his pioneering contribution to several extensive classes of new functional materials, metal organic frameworks, MOFS, covalent organic frameworks, COFS, and zeolitic imidazolate frameworks, ZIFS. Yagi established the chemical foundation of the MF field through his successful crystallization of the first MOFs with the strong bond approach in '95, where metal ions are joined by charged organic linkers, exemplified by carboxy plate, followed by the use of multimetallic clusters as a secondary building unit, SBU. The proof of permanent porosity in MOFs by gas adsorption isotherm in '98 and achieving ultra-high porosity in '99 with MOF5. His discovery of the first 2D COFs in 2005 and 3D COFs in 2007 vastly expand the scope of organic materials beyond 0D molecular solid and 1D polymers to 2D layers of COFS and 3D network COFS. He termed this field reticular chemistry and defined it as a linking of molecular building blocks by strong bonds into crystalline extended structures. Yagi has also been leading the effort in applying these materials in clean energy technology, including hydrogen and methane storage, carbon dioxide capture and storage, as well as harvesting water from desert air. He is a highly cited researcher with an H-index of 168 and over 181,129 citations. Congratulations.
Thank you, Shuji. Okay, so congratulations to Steve and Omar again. And this certainly have continued the spirit of Professor Nakamura's research on blue LED, making fundamental breakthroughs in functional materials and translate them into technology of significant potential that can actually improve our daily life. So I'll hand over to Professor Paul West to host the following program.
Very good. It's my pleasure to be able to announce the Heeger Award. These are named after Alan Heeger, our 2000 Nobel laureate in chemistry, and it recognizes exceptional young researchers for outstanding contributions in functional materials. And the constraint is that these the winners must be 45 years old or younger. Our first awards went to Julia Greer and Xiaodong Zhu in 2019. And I'm delighted, oops, we're missing I'm missing someone here. Hold on. I don't seem to have that slide. Okay, well, we'll just stop sharing and I'll talk. I'm delighted to announce the winners are two good friends and terrific scientists. We have Omar Farha, an alumnus of UCLA. Oh, we're on the wrong one. Nope, sorry. I was on the right one. I'm so sorry. Yeah, my confusion. Not enough coffee yet today. These are a little bit out of order. Yeah, here we go. So, yeah, one more espresso coming right after this announcement. Andrea Alou, founding director of the Photonics Initiative and Advanced Science Research Center and Einstein Professor of Physics at City University of New York, and Cynthia Casaraghi, Professor of Nanoscience in the Department of Chemistry at University of Manchester and the National Graphene Institute in the UK. So Professor Alou's award recognizes his seminal contributions to the realization of engineered functional materials. Yes, can you hear me?
I'm sorry for the confusion. We actually asked Professor Kostya Lovoslov to introduce our awardees.
I'm so sorry. Kostya, you're here. Fantastic.
Paul is doing a fantastic job. So even without coffee, so Paul, you're. I'm just
okay. I owe you a beer, Kostya. Off you go.
Keep listening all the time. Anyway, so yeah, congratulations for our HIGA award winners. It's this year, as Paul already said, it's Andrea Alou and Cynthia Casaraghi. So Andrea Alou gets the award for his seminal contribution to the realization of engineered functional materials and metamaterials and their applications in photonics and acoustics. And Andrea is the founding director at the Photonics Institute, as Paul already said, the Advanced Science Research Center, and he is the Einstein Professor of Physics at the Graduate Center, City University of New York. He received his PhD in 2007 from the University of Roma, and then he made his postdoc at the University of Pennsylvania. And after that, he joined the faculty at the University of Texas in 2009, and he was the Temple Foundation Endowed Professor until 2018, and then he joined the University of New York. And his research interests are really broad and includes applied electromagnetics, nano-optics, nanophotonics, microwaves, non-linearities, non-reciprocities, acoustics, optical, nanocircuits, and nano-antennas. Cynthia Casaraghi gets her award for the development of biocompatible 2D inks and their use in printed electronics and biomedical applications. And Cynthia holds a chair in nanoscience at the Department of Chemistry at the University of Manchester, and she got her master in nuclear engineering, so quite a scope here from Milan, and then a PhD from electrical engineering in Cambridge, and then she got quite a wild career. In 2005, she was awarded the Oppenheimer Early Career Research Fellowship, and then Humboldt Research Fellowship, and then Kovalevsky Award. And then in 2010, she joined the chemistry department at the University of Manchester. And she's a leading expert in Raman spectroscopy with a number of seminal papers in this area on Raman of carbon materials, but also her interests go far beyond the carbon material shift, because it's very active in the area of printable electronics and biocompatible materials. Congratulations, guys.
Terrific, thank you. Now, our next award is being given for the first time. It's named after our colleague and collaborator, Professor Sir Fraser Stoddart, who won the 2016 Nobel Prize in Chemistry. The Stoddart Award recognizes outstanding young and middle career researchers for their exceptional contributions in the field of functional materials. And if I'm not mistaken, then I'm going to introduce Professor Stoddart to introduce the awardees. Fraser?
Thank you very much, Paul. Can somebody bring up the pictures? Okay.
There we are. Yeah.
So I have the distinct pleasure of being able to introduce two of my colleagues here at Northwestern University, Professor Omar Farah, who's a professor of chemistry, and Professor Mark Hersham, who is not only a professor of chemistry, but also of materials science engineering at this university. So let's introduce Omar first of all. Omar Farah is a member, as I said, of this department of chemistry, having earned his PhD at UCLA under the mentorship of Fred Hawthorne. He is already extremely well recognized worldwide for his influential contributions to the field of metal organic frameworks, specifically in regard to the design and synthesis of new metal organic frameworks and for effectively propelling their potential for application in catalysis, storage, separations, in order to reduce energy, protect human health, and fight climate change. At a specific level, Omar Farah has designed smart materials for storage and separation of gases. He's designed smart sponges to stabilize enzymes that catalyze important reactions such as chemical warfare agent degradation and carbon dioxide reduction. He has designed highly active catalysts for chemical warfare agent detoxification by fine-tuning the structure of the metal organic frameworks. And finally, he's designed adsorbents to remove inorganic and organic contaminants from water and characterized the binding motifs by single crystal X-ray diffraction. Omar Farah is the founder and president and also the chief scientific officer, and also, on top of all that, the guiding light for Newmat Technologies. This is a company that is focused on metal organic frameworks and employs in the region of 30 people and is always looking for more employees. Newmat's expertise lies in the design and integration of MOFs into next generation storage, separation, and purification systems. Omar Farah has a quite remarkable publication record with well over 600 papers. And arising out of these publications, he's received a large number of citations, probably over 70,000, and has already an H-index of 120 or more. He is a highly cited researcher in chemistry, going back as far as 2015. He was recognized by the American Chemical Society as a Kavli Emerging Leader lecturer in 2016. He was elected to be a fellow of the AAAS in 2017. He won the Kuwait Prize in 2019, and he is a foreign member of the European Academy of Sciences since last year, and also a fellow of the Academy of Arab Scientists. Congratulations, Omar.
Thank you so much, Fraser.
Right, so now I move to Mark. Oops.
And we're delighted to announce that next year we'll have a new prize named after Kostianov-Vasilev.
Paul, this
Yes. What? Oh, did we miss?
Yeah.
You're off to Mark. Sorry. Yeah, I do need coffee.
Okay, so Mark Hirschman, who receives one of these new AAAFM Stoddard 2020 awards. Congratulations, Mark. Is the Walter P. Murphy Professor of Material Science and Engineering, and also the Director of the Materials Research Center at Northwestern. He holds faculty appointments as well in the departments of chemistry, applied physics, medicine, and electrical engineering. Mark Hirschman earned his BS in electrical engineering from the University of Illinois at Urbana-Champaign, UIUC. In 1996, an MPhil in physics from the University of Cambridge in the UK in 1997, and his PhD in electrical engineering from UIUC in 2000. His research interests include nanomaterials, nanomanufacturing, nanoelectronics, scanning probe microscopies, renewable energy, and quantum information sciences. Dr. Hirschman has received several honors, including the Presidential Early Career Award for Scientists and Engineers, the TMS Robert Lansing Hardy Award, the AVS Peter Mark Award, the MRS Outstanding Young Investigator Award, the US Science Envoy Award, a MacArthur Fellowship, an AFVS Medard W. Welsh Award, and numerous teaching and etc. awards from the department here at Northwestern. Mark is an elected member of the National Academy of Inventors and a founder of two companies, Nano Integris and Volexia, which are commercial suppliers of nanoelectronic and battery materials, respectively. Dr. Hirschman is a fellow of the MRS, the ACS, the AVS, the APS, the AAAS, SPI, and IEEE. And he also serves in his spare time as an associate editor of ACS Nano. That gives him a link to Paul. So many, many congratulations, Mark. And over to you now, Paul.
Thank you so much. Spare time. I thought that's what Mark did first every morning. So, well, thank you, Fraser, and sorry for my uncaffeinated state here this morning. Finally, I'm delighted to announce that next year we'll have a new award in honor of Kostianov-Vasilev, who you met earlier. Sir Konstantin Vasilev won the 2010 Nobel Prize for his discoveries and elucidation of the properties of graphene. And this award will recognize outstanding researchers who've made extraordinary contributions in 2D materials. And with that, I will turn it back to Professor Zhangfeng Duan and apologize for my mismanagement of the award announcements. But congratulations to all these terrific awardees, and thank you to our announcers. I'm very sorry we don't have you all here at Los Angeles to be together and be able to share this conference in person. We'll hope to be able to do that next year. Thank you all.
Thank you, Paul. Thank you, Paul. So congratulations to all our awardees. This is really it's tremendous accomplishment in both. It's indeed in both fundamental science and the technology potential for the accomplishment from all our awardees. So we are certainly grateful to Professor Nakamura, Professor Higa, and Professor Stott, and Professor Vasilev for their support of the materials community and allowing us to use their name to honor the most exceptional scientists in the field. And in particular, I'm sorry for the confusion in the morning because we have some last minute changes, and we are certainly very grateful to Shuji, to Kostya, and to Fraser for joining us after their busy schedule, and particularly Kostya in very late hours in Singapore, and to help us to honor our awardees. So I guess that concludes our award ceremony, and we'll move to our plenary speaks by our awardees and distinguished guests. And our first speaker will be Professor Stephen Dembas, our Nakamura awardee from University of California, Santa Barbara.
Hello, everybody. Thanks again to the AAAFM committee, and of course to my colleagues Suji Nakamura, but also my colleague Alan Heger and Fraser Stoddard for those great awards, and congratulations to all other awardees. So can everybody see my view graphs okay?
Yes.
Okay, great. So this work I'm going to be showing today is basically the culmination of several years' work with my colleagues at the Solid State Lighting and Energy Center at UCSB, and the work of a lot of hard students. I won't read everybody's name here yet, but really I want to focus on the three nitride materials, which, as you know, Suji invented the blue LED, which then led to white lighting. But what we now see is a plethora of applications that have now opened up with this material. And that's what I want to talk about today, is the use of three nitride materials, functional materials, for a wide range of applications. And particularly, I'm going to focus here on the micro LED application, because this is what I see as the next big emerging application area. And we've spent the last few years now developing what we believe will become a ubiquitous material for displays platform. And if time allows, I might talk a little bit about the laser diode lighting, but I think we're running about 15 minutes behind, so I'll try to keep it on schedule. So focus on this area, but just to let you know, these materials have expanded from general lighting to even in the inverter for electric cars, also inverters for photovoltaics, car headlights, and even laser projection and Li-Fi applications. So what are micro LEDs, and why do we think the gallium nitride is now going to impact that? And where we see it impacting is basically, we think it's going to impact handheld displays, because you can now make flexible, very high battery efficiencies displays in the red, green, blue. Of course, wearable displays for augmented reality is another area where it'll impact. Of course, there you could even have it in a heads-up display. And Samsung has already commercialized the larger version of micro LEDs, that is about the 40 micron dimension, for very large format TVs. This is about a 200-inch display shown at CES, and this is now available for sale. However, the cost is extremely expensive for these large format TVs. So why do we think that the gallium nitride will be the next generation display material? And it really comes down to what I call power consumption and brightness. As you can see, the incumbent display technologies of LCD have been starting to be replaced with organic LED. But one of the areas where OLED basically has a weakness is outdoor visibility and visibility for things like heads-up displays. And as you can see, the micro LED displays built with these traditional materials, but now at a much smaller scale, is basically 100,000 candelas per meter squared. So it's well viewable in sunlight and other areas. The other big advantage is energy efficiency. And we believe that the power consumption relative to an LCD display will be 90% lower than an LCD display. So this means you don't have to charge up your iWatch every night. It could probably go 3 to 4 days between charges, because the display is one of the major drains on mobile displays. And then, of course, we can see already the nitrides are doing 100,000 hours in the white lighting. So we believe we have a clear path to very long lifetimes with the micro LEDs. Okay, my slide stopped advancing. no idea why. There we go. So what are micro LEDs? So micro LEDs are basically LEDs below the size of about 10 microns. And basically, you're going to need about even smaller than that, 2 microns for augmented reality and mixed reality. So as we basically increase the pixels per inch from 2,000 to 5,000, you will go from basically 10 microns to 2 microns. And this is now a whole new technology food chain we have to develop, but it all starts with materials, as you know. So in order to reduce the size and the cost of the micro LED, we need to get to dimensions below 10 microns. And here are some estimates from Vico Corporation, which makes a lot of the MOCVD equipment used in this. And you can see the cost per display is directly related to the size. And as you can see for let's say the 4K TV here, to get the cost of the materials below the goal of $200, you need to move from the current size of, actually the current size is 40 microns. We need to move to 9 microns for the TV to get it below $200 for a TV. And for a cell phone, you needed to get it below $10. And as you can see, simply driving the size down, we can get that there if we get to 3 microns. Now, you may think that as you reduce the size, you're going to lose brightness, but actually the nitrides and gallium arsenide materials have a lot of brightness to spare. So reducing the size will directly reduce the cost, but yet not yield anything on brightness. So the material choices that we have to make these micro LED displays are basically the indium gallium nitride material system and the aluminum gallium indium phosphide material system. So we've been looking at both of these material systems. The Allen gap is what's needed for the red here, about 620, 630. So you can see it's still more efficient than the nitrides. However, we've been pushing hard on the gallium nitride materials, and we're increasing to get the efficiencies up in the green and the red. So there's still an open question on whether the red pixel is going to be aluminum gallium indium phosphide or indium gallium nitride. And one of the reasons we believe for the small displays it could be indium gallium nitride is because we still see that the red aluminum gallium indium phosphide, the efficiencies of these tank as you go to small sizes. Now, this is just going from 262 microns down to 32. You could see the efficiencies drop from 5% to less than 1% at the higher currents. Correspondingly, LG Corporation has shown that they can get down to about 15 by 15 microns, but even there you see the efficiency drops from 12 to 4%. So at these very small dimensions, it seems that aluminum gallium indium phosphide is having trouble with the defects at the surface and the surface recombination. So that's why we want to look at indium gallium nitride. And in some seminal work in the indium gallium nitride field done earlier by both Hewlett Packard and by Suji's group when he was at Nichia, he showed that the indium gallium nitride LEDs have this remarkable property that the efficiency, that is normalized efficiency here, as a function of dislocation density for the InGaN materials, remains extremely bright despite defect levels on the order of 10 to the 7th or higher. Now, this is in contrast to the more homogeneous material of gallium nitride, which is shown here, which behaved like traditional gallium arsenide materials. So, in other words, as we go smaller and smaller with these LEDs, we believe that indium gallium nitride will be a more robust material. And this basically is due, after several decades of work. One of the real magics of the indium gallium nitride is that when you look, this is with an atom probe here, at the indium fluctuations in the quantum well active region, you can see that InGaN is not very uniform and forms highly localized states which trap the excitons. So this is keeps this exciton here away from the defects. So this was an earlier paper from Suji in Nature Materials, which showed that localization in indium gallium nitride is one of the keys to getting high efficiency. And this is basically, you might think of these as random quantum dots, which help localize the excitons in this material. So really using this very fortuitous advantage of this material to make a very nice functional device is one of the key drivers, which has led to efficient LEDs in the blue and the green. Now, this shows some comparison between the early work we did in 2016 when micro LEDs first came on the scene. As you go from 100 micron size here, which is shown on the right, in the top scale, this is where we were 4 years ago. As we went from 100 to 10 microns, basically the efficiency died around 20 to 10 microns. And now that we have these improved material processes, which I'll show you the story of next, you can see that we can now get very bright emission down to 10 microns and maintain efficiency almost size independent by doing improved materials processing, both the growth, but also the chip fabrication. So let's go into that story a little. Okay, somebody needs to mute there, but nevertheless, so what are the key research things that we need to address in micro LEDs to solve these problems? Well, the key one I mentioned before is the efficiency drops as you make the size smaller. And particularly when we got to sizes below 40 microns, we could see that the brightness dropped. The other thing that we have to address is we have to go from blue now to the green and the red if we want a full color display in one material system. And the main problem there is we run into what's called the quantum confined Stark effect. There's a very strong built-in piezoelectric field as you increase the indium. And so that creates a huge blue shift in wavelength for InGaN when you make these on the C plane of the crystal. And finally, we'd like to get to transparent contacts. And one way to do that is to grow tunnel junctions, which are completely transparent to the light. And so there we've worked on addressing that issue by employing tunnel junctions for the top of the micro LEDs. So first, let's address the first issue, the size, efficiency with size, and that's shown here. So this shows you for a blue LED, as we decrease the size from 100 microns to that 10 microns, the efficiency was dropping pretty drastically from 25 to 15%. And we went about and looked at what was going on here. Basically, what we found out is that there were surface defects because the LED is now becoming so small that the diffusion length of electron holes is such that they can recombine non-radiatively on these sidewalls. So one of the graduate students in my group, Matthew Wong, helped solve this by determining that plasma etching was actually, while it's the usual method to make LEDs, it was actually damaging the sidewalls and creating defects here. So we used atomic layer deposition because that's a lot less damaging. And so he deposited ALD here before doing the PECVD step, because as you know, atomic layer deposition's done at much lower temperatures of 200 to 300, and also you get perfect coverage of the sidewalls. And so you can see here that using the ALD of silicon dioxide here basically solved two effects. Not only did it solve the brightness decrease we were seeing with the PECVD LEDs shown here in the middle row, but it also solved the current crowding effect that we were seeing with reference LEDs and PECVD coated. That is, the damage that's created just in making plasma etch and then the coating of it was damaging it. And people didn't see this for lighting because when you make a lighting size LEDs, you're at 1 millimeter. But now that we get into the 10 microns or even less, we think we can solve a lot of these problems by taking care of the surfaces and passive surfaces. Additionally, we found out that the plasma enhanced CVD was attacking the ITO interface. So here it shows you what the PECVD was doing to the indium tin oxide. And so we worked on basically perfecting a way to protect the ITO, the ITO is basically being reduced to metallic indium and tin oxide, which are less transparent. So also in reverse current, this is the leakage current of the device. That is current that doesn't go into actually creating light. We found that the reference LED, as you decrease the size, all of a sudden had huge current densities. And whereas PCD solves that problem for 100 micron LEDs, it didn't solve it for the larger. And here you can see that ALD also solves the leakage current problem that was plaguing the micro LED industry. So that in turn will help this basically decrease in peak external quantum efficiency that you see here. So the right side shows you a reference 100 by 100 micron LED. It reaches an efficiency around 42%, but when you make it smaller, 20 microns, it drops to 24%. Now, when you added PCVD to the mix, you can see the blue line here, it's damaged even further. It goes down to below 10% with PCVD. But as I mentioned earlier, the atomic layer deposition provides a much better passivation and improved the performance of the LED here in the green line to now about 30%, and shows you a nice flat EQE curve over a wide range of current densities. So combining all these things we know on the chip fabrication and with InGaN, we can see now that we have achieved very high efficiencies of 42% in the blue for 10 micron micro LEDs. And so, as I said, this is now some of the I think the brightest per size LEDs you'll find in the scientific literature. And now that the development, it has to really now focus into the green and the red. So we have these great efficiencies in the blue. We've got to get the efficiency up in the green and the red. So one way to do that is to get rid of the top ITO. And the way we plan to do that is to put a tunnel junction on top of the LED. That is, replace the ITO, which is right here with this N+ layer, with transparent gallium nitride. And so then we have a tunnel junction right here. This is the PN tunnel junction. And then you can go with a NPN structure, in which case directly above the quantum wells, there's no longer any ITO or metal. And so we'll get a nice transparent LED. Now, one of the problems when you make tunnel junctions in the nitrides, it was not as easy as gallium arsenide, because it turns out that hydrogen was not diffusing through the N-type gallium nitride. And one of the key inventions in the Nobel Prize discovery for gallium nitride LEDs was the fact that hydrogen was passivating the acceptors. So we need to get rid of this hydrogen. And the way we did that is by creating a selective area of growth that is a bunch of holes in the LED here, so that the hydrogen could diffuse out through the P layer, since it doesn't diffuse in the N layer, so that when you put the common N electrode on, you can get a lower voltage. And you can see that basically, as we go smaller in size here, that without the selective area growth or the SAG holes, the voltage was too high. The ideal voltage is about 3 volts, but adding the selective area growth here, which allows us to activate the P, you see we could drop it to about 3.2 volts now across all sizes of micro LEDs. Furthermore, we've improved this tunnel junction in addition with a chemical treatment and what it's called a multi-cycle activation. That is, you etch and then cycle the LED into basically a RTA furnace to drive out the hydrogen. And you can see that with no cycles, that is, the hydrogen is still in there. The LEDs have a very high voltage of 6 volts, but after 3 cycles, the micro LEDs with the tunnel junction are now only 0.2 volt different between the best ITO devices. But the most important thing is that the tunnel junction LEDs, which are shown in blue here, even though they have a slightly higher voltage, they're about 20 to 30% brighter than the ITO LEDs, and therefore they're much more energy efficient. And what's important is this high wall plug efficiency is seen for the tunnel junction devices here in blue, is seen at low current densities. So we get efficiencies as high as 58% here now. I showed you 42% earlier for the ITO LEDs. But what I didn't show you is that the ITO LEDs at low currents aren't as efficient as the tunnel junction. So now we have very good efficiencies over a wide range of current densities. So as you swing your display brightness up and down, you'll be able to maintain efficiencies above that 40% range. Furthermore, we now have a very transparent LED. So like we did in the lighting arena, where we started to mount not on metal, but on transparent submounts and substrates, we take the micro LED, and rather than put it on a metal or a silver header, you flip it and you put it on transparent plates. You can use alumina here, you can use sapphire or glass. You can see that you now have a micro LED display which is viewable from both sides. So it puts out light in all directions. You can also use zinc oxide for that. We call this vertical transparent packaging. And so this is now the vertical transparent packaging another iteration of LED technology, which now gives you the very high efficiencies for transparent LEDs here. You can see if you use sapphire here, it's over 85% transparent in a wavelength range. Zinc oxide is also good, but it's at about 75% transparent. But nevertheless, you can see that you get about another 30% of the light coming out when you go from a conventional metal-based submount to a transparent-based submount. So this is now a mounting or packaging technology, which not only is brighter, but it's actually viewable from both sides. So you can view, you can finally have that display in your hand, which is transparent phone that you always see on all these science movies. You can now have that hopefully sometime in the future, although I won't tell you how many years that's going to take to get it to the marketplace. We now have a true transparent display technology. Okay, the last area I think I want to touch on to keep this on track is the getting to the red wavelengths. So this is the actual full device structure. We go on what's called pattern sapphire substrates. We grow basically 6 iteration layer of 30 angstrom indium gallium nitride quantum wells. Very complex, epitaxial stack where we put aluminum gallium nitride capping on layer to protect that InGaN. I'll just show you some more traditional structures here where we're just using ITO on it. But this is now the structure of the red micro LED. So up until I'd say just a year ago, the red InGaN micro LEDs, when you made them smaller, weren't very efficient. Were less than 1% efficient. But now that we employ a lot of that chip fabrication technology along with our epi technology, we can now see that we're able to get basically somewhat size independent efficiencies in the red. So we're now up to 2.5% efficiency for a 20 by 20 micron LED, which is now getting in a realm where it can start to compete with the gallium arsenide at the smaller scales. So one advantage here is that this is all now in one common material system. So the red micro LED with the InGaN is now displaying fairly good characteristics. Here shows you the voltage characteristics as a function of size. Looks pretty good. It's anywhere from basically at 20 milliamps here. It's anywhere from 3.8 to 3.2 volts. Optical power is now exceeding a milliwatt for the larger scales, but even for the 20 by 20, we're getting 0.1 milliwatt. But you got to remember that's a very small area. This is actually more power than you need for a display by quite a margin. And the full width at half max, centered around 610, is a little broad, about 42 nanometers. So we've got to work on the full width half max here, and we also need to shift this wavelength from about 610 to closer to 630, 640. But it is displaying pretty good characteristics. Another way we hope to increase the wavelength is by going to porous GaN. So this is a new technology which just started to be developed in the last few years. So what is porous GaN? Putting basically a layer under your epitaxial stack in which you put high silicon doping, and in turn is etched with oxalic acid. And what it does is it basically gives you a compliant layer here under your growth substrate. So the growth substrate is this top layer here. And shown in here in the TEM, you can see our porous layer here. And then we're actually able to grow full device structures in this layer here. You see a V defect here, but actually we've determined the V defects are actually somewhat beneficial to the LED performance, which is kind of in contrast to what you think. But the regular device layers here actually have less dislocations than the layer that was below it. So then you put the device layer on top of the porous GaN layer, and the porous GaN layer acts as a compliant substrate. So this just shows you what that buys you in terms of wavelength. So these are 3 samples. One is just a plain wafer. One is a plain wafer with a tile put on it or a mesa. And then the sample A is the tile where you've made it all compliant. These all were grown in the exact same epitaxial run right next to each other. So traditionally they should all come out blue. But as you can see, by putting the porous GaN here, we were able to shift the wavelength from the blue to the green due to several reasons. One is it's more relaxed. When it's more relaxed, it actually incorporates more indium, which is a lower band gap. So one of the graduate students in Umesh Mishra's group use this then to get a fairly big red shift here. So grown on a non-porous substrate, it would emit in the green, but putting it on the porous substrate, we're now able to get into the red. And more importantly, the red shift, as you drive the LED harder here, was only about 35 nanometers. So we've now gotten red micro LEDs with a MESA size of around 4 microns. And that shows you here what it looks like. The only issue then remaining is we've got to make this thing brighter, and we've got to get rid of this fairly strong blue shift. So the strong blue shift in wavelength is shown here in the green. That is, as you drive the green, the color changes. Same thing in the red. The green LEDs have a blue shift of around 18 nanometers, which is somewhat manageable. But the red LEDs are still too big at 57. That's just too big of a red shift. It's going from deep red to kind of a orangish red. We've got to solve this problem, and that's kind of a future direction that we have to work on. Final thing I thought I'd show you is how do you actually make a display now that you have these materials. So this technology actually was motivated by some of the previous awardee, John Rogers' work at Northwestern, where he worked on transferring gallium arsenide materials using a stamp transfer. So taking what we saw there, we employed our own little iteration of technology, which is to, rather than to use laser liftoff, we use what's called photoelectrochemical liftoff. And photoelectrochemical liftoff is we put a layer here, this interface layer, which can be easily etchable in KOH. And so we do that. It etches in KOH when it's exposed to a wavelength of light, which is generates electron hole pairs in that. And with that sacrificial layer, then, as long as you come in and make these tiles on the side, we're able to make these micro LEDs, which can then be transferred. So you basically etch it off with the photoelectrochemical etch. The wavelength of light we use for that is 400 nanometers. And then, like I said, John Rogers had developed this transfer printing technology. So we then applied that to these wafers, and you could see that the micro LEDs then, after you've done the PC etch, can be picked up and bonded to the temporary PDMS substrate stamp here. You can see here yields pretty good, about 80%. And then you have your micro LED, which can then be stamped and transferred onto any kind of substrate. So indeed, those micro LEDs are very robust. These show you some 10, 20 micron ones. They're after transfer, they're able to show very good light and voltage characteristics. This is a blue one where we've just transferred the micro LEDs to a glass slide here. You can see you turn the glass slide on, it's very transparent, and the display is easily viewable. That is, you can look right through it, but when you turn it on, you can see you get bright light. So we've been able then to transfer red, green, and blue with fairly good wavelength characteristics shown here. Like I promised you, this will be a transparent, flexible technology. This just shows you we're able to bend this one. In this case, we put it on a plastic. We're able to then show you that we can get leads to that and get pump all 3 colors. So I believe the nitride materials, in addition to lighting, are now set to impact displays in a big way. So hopefully you'll start to see more micro LEDs for full color photonic devices start to issue. So in the work I showed you today, then we've showed you high external quantum efficiencies in the blue, and that was achieved by novel processing, novel materials, primarily employing atomic layer deposition and tunnel junctions. The blue micro LEDs are the best in the class at 58%, which, just to give you some feel, an LCD display, the current displays used for your TVs, in other words, they're about 4%. So this is like a 10-fold improvement over the current LCD displays. Of course, OLED is closer to 10%, which is a good improvement. But at least in the blue, this is a huge improvement in efficiency over traditional LCD. More work needs to be done in the green, which is only about 20%. And then we showed you red LEDs of about 2.6%. So we need a lot of work in the green and the red to get these efficiencies up so that you have an overall efficient display. So thank you for your time, and thanks again for the award. I'm very honored to receive this award. It is named in terms of in honor of my colleague. Thank you, everybody. I'm not sure if we have time for questions, or we have to keep on schedule.
Thank you, Steve. Thank you for very inspiring and a very comprehensive talk on micro LED. This can never stop amazing me. So maybe we can have one or two questions, even though we are kind of falling behind. Do we have any questions from the audience or not? I'll start with one question actually. It seems there's a trend when we reduce the size of LED because of this edge wall that reduces the efficiency. I'm curious whether we could actually make the mesa force and do architecture growth and basically to grow small LEDs, directly grow small LEDs instead of using lithography to pattern.
That's very good. Yeah, that's a very good question. So that's what's called nanorod LEDs. So people have grown nanorod LEDs, and they've been able to show light emission down to, like I said, about not super small, around 1 micron. But even there, you have a free surface, and that free surface has been shown to also have non-radiative recombination. So I think it's the fact that at a free surface you have a dangling bond. So it's the dangling bonds which start to affect it. But yeah, you are right. You could just grow through holes and just do everything through what's called selective area growth and grow the LED up that way. But you'll still have to handle the dangling bond problem is what's a limiting factor in CMOS transistors with the silicon dioxide silicon interface. So we just have to work on passivating now the dangling bonds. So probably some of the chemists in the group can think of another way to passivate, because I think that the atomic layer deposition doesn't do a perfect job of passivating the dangling bonds. It does a good job of passivating the big effects of plasma CVD damage, but it doesn't perfectly passivate the interface.
Yeah. So I guess in principle, I get there's probably technical challenges. In principle, it could grow all around it, right? I mean,
yeah. So those are exactly nanorod LEDs. So it's like a quantum rod or quantum dot. So you grow a higher band gap material, and that helps solar cells a lot when you put the higher band gap. So these are all growth technologies which we need to explore. And so there's still I'd say there's still a lot of material science to do to get the micro LED displays out there in the market.
Okay, thank you very much. Thank you very much, and congratulations again. And in light of time, we'll move on to our next speaker, Professor Omayak from UC Berkeley, also our Nakamura Award winners this year. Oma.
Yeah, it's a pleasure to be here, and it's an honor to receive the Nakamura Award. I want to thank those who nominated me and selected me for this prestigious award. I would like to discuss with you our work on water harvesting from air, and I would like to make the case that we can capture water any time of the season from air anywhere in the world. Now, this is part of our program where we're trying to address what I call the 3 stresses on our planet. One is achieving clean fuels, clean air, and clean water. We have been busy at work with using metal organic frameworks and covalent organic frameworks to store hydrogen and carbon dioxide, and very recently demonstrated that we can harvest water from desert air where the humidity is low. I want to focus on the water problem and show you our results in that direction. But concerning the 3 stresses that I mentioned, we are fortunate, chemists are very fortunate to have at their disposal the periodic table and our ability to make molecules and materials that perhaps could address these problems. I believe that we have this chemistry in hand with MOFs and COFs. But I also want to make the case that was made here in this article that devices that we will design to address these new challenges are going to be complex, and they will use the elements in much of the elements in the periodic table. So again, that puts a lot of burden, I guess, on chemists, or the challenge for chemists to develop chemistry that utilizes as much of the periodic table as possible to allow for flexibility and exploration of properties that ultimately will address these tremendous challenges. So I believe that reticular chemistry is a component of this, of addressing this challenge. And in reticular chemistry, we have addressed the challenge of linking molecular building blocks by strong bonds to make crystalline extended structures. And there are three components in this definition that are very important. One is molecular building blocks. We take well-defined units from a library of metal complexes and organic linkers to link them together by strong bonds. And I'd like to emphasize that the strong bond here is important because you want to make robust, resilient materials that are going to, let's say, be placed in an automobile or in a power plant or in a device that harvests water and be used year after year after year without having to be replenished or maintained, so that it is in the device for the lifetime of the device. The other thing that is a challenge that we have addressed back in the mid-1990s is to take those building blocks that you link through strong bonds and develop methods of crystallizing them so that we know exactly where all the atoms are and characterize these by single crystal X-ray diffraction. So the result of reticular chemistry has been metal organic frameworks. And as I mentioned, we were the first to crystallize MOFs using strong bonds in 1995, using metal carboxylate linkages. In 1998, we were first to show that they are porous. They exhibit permanent porosity by measuring their gas sorption isotherms. And in 1999, we showed that they can be made with ultra-high porosity. The MOFs, the characteristics of the MOFs is that you have metal-containing SBUs, such as in this structure, 4 zincs to make a zinc oxide unit that is linked by organic to make an extended infinite 3-dimensional structure. And we use the yellow ball to indicate the space within which gases and molecules can be captured and stored or captured through separations. The other class of materials based on reticular chemistry were discovered by our group in 2005. Those are the 2D COFs, and 2007, the 3D COFs. I won't say very much about these today due to time limitation, but I will mention towards the end their water harvesting properties. Now, I have been talking about making robust materials and rigid pores, open pores, and those are very important properties for making materials that could address those challenges. But also, we've been thinking about flexibility. How do you take this strong bond approach to make flexible materials so that you can take advantage of dynamics within extended structures? And for that, we have reported in 2016 molecular weaving, where you have covalently linked threads that are interlaced with other threads. You see them here in red and blue, weaving in and out of each other to make a 3-dimensional woven structure. These have tremendous mechanical properties that hopefully we will report on very soon. So today, I just want to make the case that the strong bond and the SBU approach, this cluster metal oxide cluster approach, where they are linked through the strength of a metal ligand bond, and the ligand here is not neutral, but it's charged, and that's what makes for the strong bond. So these cluster SBUs allow you to make frameworks that are architecturally robust and, as we have shown, chemically robust. So we have over the last 25 years, developed the chemistry of MOFs to the point that now we can talk about deploying these in devices that would harvest water. So that's the topic of my presentation today. Here I'm showing a map of the world with the water-stressed areas highlighted in colors of increasing red. So you can see that almost 1/3 of the world lives in or resides in water-stressed regions. And the question of water purity even arises in most of the world, including regions of the world where they are well watered. So there is also questions of clean. Third is that for many countries, this is a national security issue since they have to import their water from across borders. So that's the picture in 2040 is predicted to be a dire one, as you can see here in this map, is that many of the regions of the world that we thought, such as the East Coast of the US or the Midwest of the US, is expected to become a water-stressed regions because we are using much of the underground water at a rate much higher than it can be replenished. So water is a major issue, and if you live in California like I do, these pictures are absolutely terrifying. As you can see here, this is Lake Oroville that supplies almost 1 million people with water, is progressively getting lower and lower. This is a comparison, just a 3-year comparison that shows that some fingers of the lake are going dry. So fortunately, in my view, is that there is plenty of water in the air. So there is almost 13,000 cubic kilometers of water in the air at any one time. So anywhere in the world, if we can find a way of extracting the water from air in an economical, energy efficient way, then we would have created a natural resource that is recyclable. And since the water is only used and not destroyed, it goes back into the atmosphere. So this is what we've been working on for the last few years. And this is the topic of harvesting water from air is not new. It's been around since time immemorial, actually. If you type in Google harvesting water from air, you'll get machines like this that claim to do that. And if you look in the fine print, they claim that they can harvest water even at very low humidity. But in fact, that's not true. What is true is that these systems that work on direct cooling of air can only work on humidities that are around 60% relative humidity or higher. And that cooling air, of course, is an energy intensive process. So we need materials, systems that can work at lower humidity, where much of the world experiences lower humidities than 60%. And in fact, the desert regions of the world typically have relative humidities of around 30% or 20%. Sometimes even in the middle of the summer at midday, you can experience relative humidities of 10%. So there are no materials that can actually do that. Materials that can harvest water under those desert conditions. The point that I want to make is that if you could make materials that capture water from low humidity, where you see here in red, then those same materials will work at higher humidity. In fact, they would work extremely well at higher humidity. So the challenge is, how do we find materials that do that can harvest water from air in those red regions? Because if we could do that, then our vision of bringing water to areas of the world, anywhere in the world at any time of the year, regardless of the season or the time of day, that we can water the world using this idea of harvesting water from air. So where are we today? Before I get to the results, I want to show why is it so challenging to harvest water from air, especially by cooling, okay? Like those machines that I showed you. Now, the red regions of the world, the water-stressed regions, are illustrated here or colored on this psychrometric chart in pink, and in the green you have the humid regions. But you see here, this is a plot of the water vapor in air in grams per cubic meter, plotted versus temperature, and you see here the lines of humidity, relative humidity 10%, 20%, and so on, up to 100%. If you hit this line, then you'll make liquid water. So let's imagine that I'm in a city that has the following conditions. It's 30 degrees Celsius at 20% relative humidity. Now, if I was going to obtain the water from this air, harvest water from this air, I would have to cool down the air down to 4 degrees Celsius to be able to obtain liquid water. And that's just refrigeration temperatures. So that's energy intensive, it's not practical, it cannot be deployed on a wide scale. However, if you imagine, let's say a moth or a porous material that programmed to take up water from this low humidity, now I have water concentrated inside the pores. And in a way, I've turned this very low humidity into very high humidity. And to get the water to condense, I only need to reduce the temperature by a few degrees. And therefore, this has the potential of being an energy efficient material and hopefully for widespread use. That's really how the MOF works. It takes, let's say, desert air and turns it to a tropical air by increasing its humidity by virtue of the fact that the MOF can take up the water from low humidity. So, as I said, there are materials out there that are being examined for this application. And there are three basic requirements that a material must meet in order to be a water harvesting material and to carry out this operation in an energy efficient way. Zeolites obviously can extract water from very low humidity, okay? But they don't have high capacity. And because the water sticks into the pores of the zeolite very tightly, it makes very strong interactions with the zeolite. You can't take it out very easily. And so the kinetics is very slow. If the kinetics is very slow and the capacity is very low, then your cycle time is very long and you're not going to be able to harvest a lot of water. But also you have to put in a lot of energy to get the water out. So that's not good. As I said, they work at low humidity, but nevertheless, they suffer from these issues. Polymers, hydrogels, even molecular solids, hygroscopic, let's say solids, can have high capacity, but again, the interaction of water to these systems is very strong, and many times these don't work at low humidity. So those are, if you get a red X, then that means that it's not possible to apply these materials in an economical way. Salts have been used for a long time towards this application, but never commercialized because of these issues, capacity and strongly bound water. So now MOFs, the fact that MOFs have these metal oxide SBUs mixed with organics to make extended crystalline structures allows you to modulate the polarity that is brought in by the metal oxide unit with the hydrophobic nature of the organic in this case. So we initially discovered that we can harvest water from air using this MOF 801. MOF 801 exhibits a knee-like isotherm. You see here, this is a plot of the amount of water in cubic centimeters per gram plotted versus pressure. And you see here that at almost 20% relative humidity, you see a very nice sharp uptake of water. And the amazing thing is not just that the shape is a knee-like shape, indicating a cooperative uptake of water, but the fact that it's knee-shaped means that you can maximize your working capacity, the amount of water that can go in and out during a cycle. And the second very important aspect of this is that we discovered that we can take the water out of the pores at a very low temperature, 45 degrees Celsius. Well, this gave us the idea that perhaps in a desert environment, you could take this moth at night where the temperature is lower, humidity is high, and during the day, by heating from the sunlight, you can remove the water from the pores. And this is something that we pursued. And you can see here that you can take water in and out of the pores repeatedly. In this case, we're showing 80 cycles with absolutely no imprint or no degradation of the behavior of the material. So the material is stable in water. We also noticed that after the first cycle, the capacity drops slightly. And we wanted to look at why that is the case. Like what is happening in the pores that causes this drop of water uptake. And so we did neutron, single crystal X-ray diffraction and neutron diffraction to look at incremental amounts of water that have been introduced into the pores. So you see here the first water molecules are bound to the metal oxide unit. And then they build up what I call and what we believe are seeds of water. So these are different structures of water that form at the beginning of the water harvesting cycle. And it's these water molecules that stay in the pore while you're cycling, but their function is more like a seed function where the other water molecules that filling the pores bind to these initially, and that's what gives you the cooperative behavior in the isotherm. So we don't like to take these out and put them back in during the cycling. We leave it in the pore and only work with the water that is bound to them rather than these water molecules that are bound directly to the metal oxide units. So we wanted to take this outside the lab and show that in fact, at relative humidities of, in this case, we targeted 25 to 30% relative humidity to show that in fact this works outside the lab. And we made, in collaboration with Evelyn Wang, a mechanical engineer at MIT, we made a device that is basically a handheld device equipped with 2 grams of moth. Okay, this is a schematics of the device. Basically, you have the moth is in this box, and at night it's exposed to the atmosphere. Water goes into the moth, and during the day you close it. You expose the moth to the or the box to the sunlight, and as the inside of the box heats up, you see here going from 50 degrees to 66 degrees, you see droplets of water that are forming on the moth. Okay, not a lot of water, but we only use 2 grams of moth, and the amount of water is proportional to the amount of moth that you use. Nevertheless, this showed for the first time that in fact you can harvest water from low humidity with only ambient sunlight as an energy source. So this was a very exciting discovery, and we wanted to move this and show that in fact this also works in the desert. So this was tested in the Arizona desert, and you can see here very visibly the droplets of water that form using the process I just described. We wanted to show that in fact you can have a cup of water out of this moth, and we scaled up the moth to kilogram quantities and designed a device where you have a box within a box. The internal box has the MOF powder in it, and the outside box is open during the night to allow desert air to go into the MOF. And then during the day, it's closed to allow the interior to be heated under sunlight. Water comes out of the pores of the MOF and hits the surface here, condensing at the bottom. And then it's collected. I just want to comment that eventually the MOF will not be used as a powder in these applications. It will be used in a form like a blend or as pellets, so that we can pass air through the MOF without the MOF flowing everywhere. So this is what the device actually looked like. It's just made from plexiglass, very cheap materials, and it turns out that this device we took to the Arizona desert, and in one cycle we can harvest, depending on the conditions, 200 to 300 milliliters of water, just for one cycle of uptake and release. And this, you can see the water collected here in these vials. The water is pure. We tested the water for any contamination, including metals and organics. And needless to say that the MOF itself is a molecular filter, because it only allows water into the pores. Anything larger than water does not go into the pores. And so, so the water that we harvested is pure. Ready, and Eugene here has volunteered voluntarily to drink the water. The water is distilled. Nice. It's not mineralized, and to actually make it for drinking, you have to mineralize it, just like the water that you drink at home is mineralized. So that's a straightforward process. The MOF that I just showed you is a zirconium MOF, and zirconium is expensive. So the nice thing about reticular chemistry is that once you discover an interesting property, you can take it to the next level towards commercialization by using, in this case, an inexpensive metal like aluminum. And so again, we made an aluminum MOF. Aluminum MOFs are not known for their water stability, but this one is ultra stable in water because of these metal oxide rod units that basically have a conformation that shields the metal ligand bonds from any hydrolysis. And so this MOF CO3 is extremely stable in water. And even before I show you the device, it's being tested over 30,000 cycles of uptake and release with absolutely no imprint left on the MOF. So the MOF can stay in the device for really the lifetime of the electronics in the device, which is 5 to 6 years. But it's made from this rod SBU and this simple pyrazolate linker to make an extended porous structure that has 1D channels. And the uptake of water in this structure is, as you see here, 330 milliliters per kilo. So that's basically the amount of water that you harvest per cycle at low humidity. And actually the great thing is that it also shows an isotherm where you take up significant amount of water at relative humidities of about 10%. It's plotted here against some zeolites, but as I said, although zeolites take up water from low humidity, it's very difficult to remove that. You have to heat up zeolites to over 100 degrees Celsius to remove the water, so that's not very economical. But the MOF composition, being inorganic and organic, allows you to modulate the hydrophilicity of the pores so that you have the right binding energy to be able to remove the water. This is another MOF that we are comparing here. This one takes up water at 20% relatively. This one is the MOF that I will show you how its properties are quite superior to any other MOF in that It can take up water at low humidity, and you see here the kinetics quite rapidly. And the nice thing is also that it can desorb very quickly. Okay, so this is the kinetics at different temperatures. And that means that if you're going to cycle this, instead of just day and night cycle, if you want a power device, now you can do many, many cycles. And so if your cycle is only few minutes, then you can do many, many cycles during the day and harvest significant amounts of water. So that's what we aim to do here with this another prototype that we designed in our lab, made from MOF cartridges that were designed to take up water. Certain cartridges take up water while the others are releasing the water. This was a powered device. And this is the results. You see here, I want you to focus on this panel and this panel. This panel is the amount of water that has been harvested. Exclude the first bar because that's the water that was in the MOF from Berkeley. But this is the water that was harvested in the desert, in the Mojave Desert, which is the driest desert in North America. And this is the humidity levels measured during the day and night. And you see that even the humidity dips down to 10% relative humidity, it can still harvest water. Okay, and that is unique to MOFs. No, and do the cycling efficiency. So I think this is a movie that shows dripping water that is being harvested from air directly from this device, which is powered by a solar panel. And the solar panel, what it does, it powers a fan that pushes air into the MOF and a heating element to desorb the water. So this is the result of this was to do few cycles a day, not so many, but even with few cycles, we were able to harvest 1 liter of water per kilo of MOF per day. So this then has been very exciting development. I already showed this data on the kinetics, which is going to allow us to do multiple cycles per day. And this is the next, this is the 3rd generation prototype. This is an electrified device based on MOF 303. And we can do not just 2 cycles a day or 3 cycles a day, but we can do 220 cycles a day using this, this device. This device deploys not 1 kilogram of MOF, but 200 grams of MOF. And from 200 grams of MOF, we can harvest 4 liters of water. If you want double that, then you double the amount of MOF. And so this then allows us to, I guess I have a movie here of the, I don't know if you can see this, but I'll just play it. There is a door in the device that allows the air in. The air goes through a module that has the MOF, and you can see some condensation there. Water will be collected at the bottom of the device. See here, a puddle of water as you are cycling the water in and out. And here's the collection of a liter of water. And as I said, 4 liters per day based on 200 grams of MOF. Needless to say, the MOF is stable and it's been cycled in this prototype for over 30,000 cycles. The water is pure and meets the OSHA and the EPA requirements for drinking water. So based on those results, we have moved the idea of water harvesting from desert air in terms of productivity just in the last 5 years to go from almost negligible amount of water collected to about, we are approaching now about 80 liters per kilo, but the capacity should go up to 100 liters per kilo of MOF per day. So if based on all these results and the progress that we have made in the design of the material, you can, just like we did with the Mojave Desert, you can calculate how much water could be collected in various climates around the world. And the most driest desert in the world is the Atacama Desert. And you can see here, even at the worst weather conditions, you're still harvesting around 10 liters per kilogram of moth per day. This applies clearly to the Mojave Desert. And we plotted different areas of the world to show that, in fact, that you can harvest water in almost every part of the world at any time of the year. And I mean, in the most driest areas like Riyadh, Saudi Arabia, or let's say Los Angeles, you get significant amount of water. You're getting about 40 liters per kilogram of moth per day. So in the last minute or so that I have, I want to leave some time for questions. I just want to say that we have a collaboration with Laura Gagliardi and her group and Joachim Sauer to try to compute the positions of where the water is going in MOF 303, but also Nikita has been very successful in obtaining single crystal X-ray diffraction that shows where the water molecules are residing for this MOF. And what I like to say briefly, that based on where the water is located in the MOF, in MOF 303, we can successfully shape the isotherm by varying the linker composition, by basically replacing a nitrogen with a sulfur in this position or oxygen, and therefore modulate the binding energy, modulate the strength of the water binding in the pores. And that's really the power of reticular chemistry. So the red shows that, in fact, unlike in MOF 801, here the organics are the binding sites, the initial binding sites of water, shown in red. The water molecules that we have located using X-ray diffraction is shown in red. And you see different stages of not just the seeding that I described, but clustering and networking of water molecules. So the water here, this is only the water structure illustrated in different colors to show the seeding, clustering, and networking stages. Now, based on these results, we can modify the isotherm from this isotherm where you have a little bump here into a smooth isotherm to maximize the working capacity at different humidities by simply changing the pyrazolate to this furan linker. Not only can we make just the furan linker MOF, but also we can make mixed furan and pyrazolate without changing the structure, but changing the modality of water adsorption sites. The result of this mixing of linkers in the MOF allows you to modulate very precisely where you want the MOF to take up humidity and to modulate the binding strength of water uptake. And this is more done not necessarily to modulate where the water is taken up at water humidity, but also to modulate the temperature at which water can be removed from the pore. And what I really want to say here is not only we're shaping the isotherm, but we're making pinpoint changes that chemists may think are trivial, but in fact, they translate into big differences in productivity and energy savings in the device level. I think that that's an important thing to keep in mind, is that very tiny changes that chemists make, let's say in this MOF 303 structure, without changing its structure, you're making tremendous changes in terms of desorption energy, desorption temperature, and the energy efficiency of the device. So I would just want to say that we have been working on covalent organic frameworks, and I won't describe the structure that exhibits this also another beautiful water adsorption isotherm. In this case, it's taking up water at 35 degrees, relative humidity of 35%, and you can do it repeatedly. These are stable structures in water. I think that's the part of the future of water harvesting, is that you can use the all organic and in our lab, carbon-carbon bonded backbones to be able to harvest water from air. And if you're worried that we're going to be using and drying the world, there's plenty of water in the air. As I said, if we serve every person on our planet 50 liters of water, we would have only used 0.002% of the water in the atmosphere. So I know I get a lot of questions that we're going to dry the world, and of course the answer is that there's plenty of water and the water is recyclable. I think on a fundamental level, we're giving the individual water independence. That in fact, when this becomes available commercially, you can have your own device generating your own water from your own air. So I would say that this is giving you independence from countries, for example, in terms of the national security, but also the individual in terms of personalizing their water. Okay, well, finally, I want to acknowledge, in addition to those that I've acknowledged during my presentation, my wonderful group members and our collaborators and funding partners. And I want to thank you for your attention. And it's an honor to receive the Nakamura Prize. And this is a wonderful surprise for me. So I'm happy to answer any questions at this point. Thank you.
Thank you, Omar. Thank you for the beautiful talk. It certainly addresses one of the most pressing problems of the world today. So we can have one or two questions. I guess I'll start with, appears like for the harvesting and particularly for the desorptions, appears like it still relies more or less on evaporation. I'm curious, you obviously have shown us you can tune the molecular linkers to change their absorption at different humidity. So I'm curious whether we could basically inspiration from a freezer stud or from our colleague Jeff Zink, they use molecular machines to change the interaction with the other chemicals, or in this case, can we actually use molecular machine to change the interaction with what molecule, activable molecular machine, for example, use photoactivable molecular machine to change the interaction, and without the evaporation, just you could somehow just directly release the water out. Without, in that case, we don't need that actual energy input.
Yeah, I mean, that's a great idea, and it's using a stimulated or stimulation using sunlight, or using a photoactive way of removing water would be nice. I think when you are at a stage where you're trying to commercialize I think that's an important direction for basic science, and it's something that some of my students are thinking about. What, instead of heating, could we use light, let's say, to break bonds or to stimulate the removal of water, and therefore get a much more energy efficient water harvesting cycle. We're not there yet. We're at a stage where we're very happy with the water efficiency in terms of commercialization.
Mm-hmm.
And the reason we heat it up is because we want to do many cycles during the day. But as I showed, you can just use ambient sunlight if you want. The water harvesting could be entirely done passively. Okay, so that just depends on how much water you want to produce. Right? So if you have a kilogram of moth passively, you could harvest a liter of water. And the moth can stay in a corner, sitting there harvesting water day and night for many, many years. So your investment is just the cost of the moth. And in this case, it's an aluminum moth. It's a cheap moth. Okay, so I think you have the option of doing it passively. I showed you that, but I also showed you that, in fact, with some energy input, you can do many 200 or more cycles to harvest significant amounts of water. So that propels us in a different regime in terms of supplying water. I like the ideas of stimulated release of water, and it's not out of the realm of possibility, and it's not something that we're not working on right now.
Okay, thanks a lot. So I guess in that of time, we'll move on. Thank you, Amma. So we'll move to our next speaker. I think next speaker is Professor Mark Hossam from Northwestern University, and Mark is our inaugural study award winner today. Mark.
Great, Jean-Ping, thank you very much for the kind introduction. It is a great honor to receive the Stoddard Prize. I'd like to thank the selection committee. And in particular, it's a great honor to be awarded a prize named after one of my most distinguished colleagues here at Northwestern University. So thank you again. But I know we're a bit behind time today, so let me jump right into my talk, which you can see is entitled Chemically Tailored 2D Materials for Electronic and Energy Technologies. So since I'm the first speaker today talking about two-dimensional materials, so let me briefly introduce them for those of you who don't think about them every day. It's customary to begin with graphene. That was, of course, the first 2D material to be isolated. And graphene is a single atom thick sheet of sp2 bonded carbon, famous for its high charge carrier mobility and interesting and unusual physics resulting from its linear dispersion relation. It's important to note that graphene is isolated from graphite, and it can be done so via a variety of exfoliation methods. And it's enabled by the fact that the bonding between the layers in graphite is van der Waals bonding. What's important to note is that these van der Waals solids go well beyond graphite to many other materials. And utilizing very similar methodologies as was used to exfoliate graphene from graphite, you can achieve those other layered materials in the 2D limit, including materials like hexagonal boron nitride that are electrically insulating, molybdenum disulfide, which is a relatively wide band gap and typically N-type doped semiconductor, phosphorine, which is the phosphorus analog of graphene derived from black phosphorus, which is a narrower band gap, typically P-type doped semiconductor. And it's also possible to take elements that are not layered in the bulk and still realize them in the two-dimensional limit by growing them directly on suitably chosen substrates. And 2D boron or borofene is an example of that. And that material is metallic. The bottom line here is that this family of two-dimensional nanoelectronic materials encompasses all electronic properties from insulating to metallic and all semiconducting band gaps in between. And as a result, if you can assemble them into heterostructures, you should be able to realize any and all electronic device functionality. But the opportunity is even greater in 2D materials in that you can also use chemical methods to further tailor and enhance their properties. And in this review article that we recently published, we went through and looked at a variety of means by which molecular functionalization can add value to 2D materials. And the reason that this works is that 2D materials are all surface, and as a result, anything in contact with them will have impact on the resulting properties. It's also important to note that the bonding between 2D materials is van der Waals bonding, and that chemical reality implies that the construction of heterostructured devices are not constrained by epitaxial lattice matching. And this will allow you to realize a very large number of permutations for 2D material-based heterostructures. And finally, since one of the methods for exfoliating 2D materials from their layered bulk crystals can be done in solution, this implies that solution-based chemical processing will provide a pathway to scalable nanomanufacturing as long as you can preserve the electronic properties following that solution processing. And this latter point is where I'll begin my talk today and describe how we can utilize methods such as additive manufacturing to formulate inks, which are electronically functional based upon these two-dimensional materials, and how we can print them to realize scalably produce electronic and energy technologies. And then, if time permits, in the second half of my talk, I'll go into the utilization of not individual 2D materials, but rather heterostructures of them to explore opportunities in next generation technologies such as neuromorphic computing and advanced energy storage solutions. So without further ado, let me jump in and begin by introducing how we achieve additive manufacturing based upon these 2D nanoelectronic materials. And so the vision that we have is to realize 2D electronic material inks. And as I just noted, the 2D material field has already demonstrated superlative properties and device prototypes based upon idealized research samples, often realized using micromechanical or Scotch tape based exfoliation. And while that is a very nice method to do fundamental physics and device prototyping, I would contend that it's not particularly scalable. On the other hand, if we look in the field of printed electronics, it's already now well established that you can achieve roll-to-roll additive manufacturing based upon organic and nanoparticle inks. And so what we would then like to do is to unite these two fields, and in particular realize 2D electronic material inks that allow us to take advantage of scalable additive manufacturing while preserving the superlative electronic properties of ideally exfoliated 2D materials. And so that leads to the delineation of a series of 2D electronic material ink design goals. The first is exfoliation. We're going to be in solution peeling away layers of 2D materials from their bulk layered crystals. And in that process, we want to be able to optimize the exfoliation yield, the throughput, and the resulting control over the size and shape of those flakes. Secondly, we need to formulate inks. We're going to have to engineer appropriate solvents and stabilizing polymers that enable printing with a wide variety of printing methods while maintaining adhesion to substrates and mechanical flexibility to enable roll-to-roll processing. Because the printed features are going to be much larger than the sizes of the constituent flakes, what you're going to have are percolating networks, and the morphology of those percolating networks will have significant control over the resulting properties. And as a result, you need to control that morphology via appropriately chosen solvent evaporation strategies and other additives that control the drying process. And then finally, again, reiterating the point that we have percolating networks of 2D flakes, the interfacial contacts between them will be important, and in many cases, the most important factor in determining the final electronic properties. For example, in a conductive ink, you want to minimize interfacial and contact resistance. In a dielectric ink, you want to maximize capacitance and minimize leakage currents. And in a semiconductor ink, you want to maximize mobility and switching ratio into technologies such as field effect transistors. And what I want to stress is that while there's a lot of work going on in the world today in each of these topics in isolation, ultimately all four have to be met in order for you to realize the best performance in your final application. And so today we're going to talk about how we concurrently pursue all of these ink design goals. Beginning first with exfoliation. And the exfoliation problem is one that's quite popular now in 2D materials, but it's a problem that's been around even longer than that, going back to the days of 1D carbon nanotubes. When these materials were being synthesized, they would typically come out of the reaction chamber in the form of bundles. And step one was to exfoliate or debundle or deaggregate these bundles into individualized carbon nanotubes. And that is often achieved in solution, utilizing agitation such as sonication or shear mixing, and appropriately chosen surfactants to enable dispersion in a wide variety of solvents. But even once you've achieved that individual nature of your carbon nanotubes, you still have an issue that you have a variety of diameters, lengths, chiralities, all of which will determine the resulting electronic properties. And as a result, after the exfoliation, you have to do a separation step, which not only eliminates the bundles or the aggregates, but also isolates your individual nanomaterials of same size, shape, and therefore properties. And what we realized over a decade ago is that the size and shape of nanomaterials is very similar to biological macromolecules. And as a result, separation methods from biochemistry can be applied to this problem. Techniques such as density gradient ultracentrifugation allow you to separate nanomaterials by their buoyant density and therefore by their size, shape, and properties. What I want to stress is that while this work initially was achieved with carbon nanotubes, over the years, we've shown that it can be generalized to virtually any nanomaterial. This would include metallic nanoparticles, where you can separate them by size, shape, and plasmonic properties, and all the 2D materials that I mentioned before, including graphene, transition metal dichalcogenides, hexagonal boron nitride, black phosphorus, and so on, can all be isolated and separated by their thickness, which is usually the most deterministic in their properties, but also by their lateral size, which can be important in some applications. I also want to stress that the methods by which we are doing this are derived from biochemistry. Biochemistry has great incentive to scale up these technologies, in particular for pharmaceutical applications. And as a result, that scale up strategy can be adapted to nanomaterials and has been done so by NanoIntegris, which is a company that spun out of our lab. This company scaled up the density gradient ultracentrifugation process by 10,000-fold and has been distributing these highly monodisperse nanomaterials globally for over a decade. What I want to stress, though, is that while NanoIntegris can sell you a very highly monodispersed powder of nanomaterials or an aqueous dispersion of them, they're not really selling you an ink directly, in that the viscosity of those aqueous dispersions is incompatible with most printing methods. And as a result, what you really need to do is to take those highly refined exfoliated powders and reformulate them into inks utilizing solvents and stabilizing polymers that are widely used in additive manufacturing. And one of those solvents is alcohol, such as ethanol. And if I were to take a highly monodispersed graphite powder and try to disperse it in ethanol, you would see a very low loading. The reason being that there's a surface energy mismatch between the graphene and the ethanol solvent. And as a result, you need to add another component to the ink, such as a stabilizing polymer. One of our favorites is ethyl cellulose. And ethyl cellulose will now allow you to increase the concentration in graphene in alcohols by 100-fold. And at these high solid loadings, you can control the viscosity of the resulting ink by over 4 orders of magnitude, allowing you to dial it in for your favorite printing methodology. For example, if you have an inkjet printer in your lab, you can dial in the viscosity to match that of your inkjet printer. And when you print the resulting graphene inks, you get very well-defined structures with no evidence of coffee stain or other drying effects. I will note, though, that upon printing, you have not only graphene present, but also the ethyl cellulose stabilizing polymer. And that stabilizing polymer is not electrically conductive. And as a result, you need to do a post-deposition curing step in order to pyrolyze the ethyl cellulose, decomposing it into an sp2-rich amorphous carbon that will facilitate charge transports between the graphene flakes and the percolating network. And this can be done under thermal annealing conditions of about 250 degrees C for 30 minutes. This is compatible with some flexible substrates such as polyimide. And if you do so, you get a very low resistivity or equivalently a high conductivity. And importantly, that high conductivity is maintained following repeated flexing or even folding of your flexible substrate, and therefore perfectly compatible with roll-to-roll manufacturing. Of course, what is not ideal for roll-to-roll manufacturing is 250 degrees C, since there's many flexible substrates that cannot tolerate this temperature. And the 30 minutes of curing time is also non-ideal, in that you'd like your roll-to-roll manufacturing process to go as quickly as possible, and you'd rather not stop it for 30 minutes just to do a curing step. And as a result, the way that this is done nowadays in our lab is rarely with thermal annealing, but rather with photonic annealing. Utilizing a pulsed xenon lamp, you can create a broadband light source, which is selectively absorbed in the graphene layer, not in the underlying substrate. And as a result, only the graphene layer gets hot, the substrate remains cool, and this allows you to pursue other lower temperature polymer substrates such as PET, PEN, paper, and so on. But perhaps more importantly, from a manufacturing perspective, the time scale of this pulsed xenon lamp is at the millisecond scale. So 1 millisecond of this pulsed xenon lamp gives you the same curing as 250 degrees C for 30 minutes. And as a result, the curing time is now faster than the printing time itself. And consequently, your roll-to-roll manufacturing line does not need to slow down for the curing process. And this has dramatic implications for downstream processing and scalable manufacturing. So to give you one example of where we use these printed graphene materials is in the area of electrochemical biosensing. And the reason that we targeted this application is that printed graphene, while it is pretty conductive, it's not as conductive as a printed metal like silver. But the advantage that graphene has over most printed metals is that it is stable in a wide variety of environments, including corrosive environments. And as a result, you can put your graphene electrodes in a salty water solution and they maintain their electrical conductivity. And of course, that saline solution is where you're going to be doing biosensing. And consequently, we now utilize our graphene inks to make interdigitated electrode arrays. And if you use methods like electrochemical impedance spectroscopy, you can tease out what component of the impedance comes from the solution versus the electrodes versus the interface between the electrodes and the solution, the so-called charge transfer resistance. And that component will, of course, can be strongly affected by any adsorbates on the surface. And if you put down an adsorbate, which was designed to react with a target analyte, then upon binding to the target analyte, you'll see a further change in that charge transfer resistance, which becomes an electrochemical readout of the binding event. And this works quite effectively in a wide variety of contexts. Recently, we've looked at cytokines for immune system monitoring, histamine for food safety. You can do this for COVID-19 detection, and we're currently working with the CDC to scale up this technology for that particular application. And again, just to drive home the point, the broad rheological tunability of these ethyl cellulose-based inks allows us to not only achieve inkjet printing or aerosol jet printing, but also gravure printing, screen printing, even 3D printing, all of which have been commercialized by Millipore Sigma. You can see the catalog numbers here. They're available. Anyone in the world who wants to work with these graphene inks can place an order and have them for testing in their own laboratories. But what's important to note is that this ethyl cellulose not only disperses graphene in ethanol, but essentially any 2D material. For example, if you want a semiconducting ink, you can replace your graphene with moly disulfide. Just like in the case of graphene, by changing the solid loading in your ink, you can tune the viscosity to enable compatibility with a wide range of printing methods. In this case, I'm showing you inkjet printable moly disulfide patterns on two very different substrates, namely glass and polyamide, and in both cases, you don't see any issues with coffee stain or other drying effects. Just like with the graphene inks, the printed structures as printed have the ethyl cellulose polymer, but that can be removed via thermal or photonic annealing. And if you do so, what you get is a semiconducting printed structure, which is suitable for a variety of semiconducting applications, such as photodetectors. And in this particular case, the active region of the photodetector device is printed MOS2. The contacts are printed graphene. So everything here is printed and can be cured at the same time using either thermal or photonic annealing. And just like we saw with the graphene, the properties of the printed MOS2 are invariant upon mechanical flexing and therefore perfectly compatible with roll-to-roll additive manufacturing. What's interesting, though, in the case of MOS2 is that the way in which you do the curing has some pretty significant implications for the resulting device properties. Specifically, what I'm showing you here is a plot of the responsivity of the photodetector versus the time response. And what you can see is that if you use thermal annealing labeled TA on this plot, is that you get a very fast time response, but a relatively modest responsivity. The reason for this is that the thermal annealing process is relatively slow. The volatilization of the ethyl cellulose is done in a very controlled manner, which leads to the morphology of the printed flakes being very ordered, sort of like a deck of cards type stacking, which maximizes the contact area between the flakes. And that gives you the best charge transport and therefore the fastest time response. On the other hand, if you do a photonic annealing, which is labeled PA here, photonic annealing releases all the volatile byproducts of the ethyl cellulose decomposition in 1 millisecond. It's almost an explosive process. This leads to a much more porous microstructure that compromises the flake-flake contact area, which will slow down your time response, but the increased surface area of that porous structure actually gives you pretty dramatic enhancement in the responsivity. The bottom line here is that the final properties depend not only on the quality of the raw material, the quality of the ink, the ability to print it, but also the curing and the influence it has on morphology can have dramatic effects on your device performance. The last example I'm going to show is hexagonal boron nitride. It can also be dispersed with ethyl cellulose. You can also vary the viscosity by orders of magnitude by varying the solid loading. You can make inkjet printable inks, which will give you very thin hexagonal boron nitride, which may be suitable for gate dielectrics and transistors. Or you can go to the very viscous limit, where you can direct ink right or blade coat. And in that very viscous limit, you get much thicker films on the order of several microns, as you can see here. You can then, of course, do curing to remove the polymer. And if you do so in a high polymer loading limit, what you result in is high degree of porosity resulting from the points where the polymer used to exist in that film. And this electrically insulating porous network is now suitable for a variety of filtration and membrane type applications. And in particular, it's well suited for separators and lithium-ion batteries, in that the hexagonal boron nitride is electrically insulating, preventing shorting between the electrodes, but porous to allow your electrolyte to seamlessly move through it. And so the question then becomes, in that context of lithium-ion battery separators, is there a competitive advantage for a boron nitride-based separator versus a traditional polyolefin-based separator? And I would contend that the most important advantage you gain is enhanced thermal stability. The issue is depicted in these photographs you see here. If I take a traditional polyolefin separator and expose it to an open flame, you can see readily catastrophic degradation of that polyolefin separator. Indeed, in a lot of thermal runaway events that lead to catastrophic failure of lithium-ion batteries, it is the separator that is failing, leading to shortening between the electrodes, which just amplifies that thermal runaway process. In contrast with hexagonal boron nitride, which is much more refractory, much more thermally stable, you can see exposure to the open flame has little to no effect on the separator. And consequently, these types of separators can dramatically improve the safety of lithium-ion battery technology, which is, of course, important in many applications. Okay, so hopefully I've convinced you that there are indeed scalable methods for producing electronically viable 2D material inks. The question then becomes, can we do things that are even more sophisticated, moving from individual materials to heterostructures to enable even more sophisticated device applications? And so what I'm going to be discussing today are two of the many applications we're pursuing in our lab. Specifically, I'll be focusing on neuromorphic computing and printed electronics and batteries. For those of you who are interested in other ongoing efforts in our lab, we're also looking at applications in quantum information science and polymorphic heterostructures. These two review articles here would be an entry point into that type of work in our lab. But due to limited time, let me just focus on two examples, beginning first with neuromorphic computing. And of course, the goal in neuromorphic computing is to mimic the computing that occurs in the brain. And what the brain consists of is neurons and synapses. And neurons, of course, have an action potential, which is a spiking-like response. And so the question is there an opportunity to utilize these 2D materials and heterostructures based upon them to realize spiking-like responses in artificial neurons? To do this, we're going to use a heterojunction device, which consists of N-type molybdisulfide and P-type single-walled carbon nanotubes. This device is one where we can gate it from either side, either the molybdisulfide side or the carbon nanotube side. And the fact that we have atomically thin materials implies that we have weak electrostatic screening. And consequently, this p-n heterojunction can be strongly gated. And that will allow us to tune the nonlinear device characteristics in manners that cannot be achieved with bulk semiconductors. And in particular, what you get from this dual-gated p-n heterojunction is a so-called anti-ambipolar or Gaussian transfer curve. The reason that you get this transfer curve is that at high negative bias, you're fully depleting the N side of the junction, turning the device off. At high positive bias, you're fully depleting the P side, turning the device off. Only at low gate bias do you get transport through the p-n heterojunction. But because we have a dual gated device here, depending upon the biases you apply to each gate, you can gain full control over the Gaussian response. You can tune the peak height, the peak position, the peak width. And that full tunability over the Gaussian transfer curve now allows very efficient pathways to realizing spiking-like responses that mimic the behavior of biological neurons. And that's shown here. If we take one of these dual-gated p-n heterojunction devices, integrate it into a relatively simple circuit using common circuit elements like resistors, capacitors, and conventional field effect transistors, you can indeed achieve a spiking-like voltage response that very closely mimics the action potential that you see in biological neurons. The beauty, though, of this circuit is that just by tuning the voltages to the two gates in your p-n heterojunction, you can dial in a wide variety of spiking behavior, including varying the timing of that spike, how many spikes you get, the spacing between them, and so on. And as a result, that provides many options for artificial neurons, competitive learning, and spiking circuits, which go well beyond what is easily achievable using conventional CMOS technology. But that's just half the story. In a neuromorphic circuit, you need to have connections between the neurons, the so-called synapses. And in most implementations in solid-state synaptic devices, you utilize a device known as a memristor. This is a resistor that remembers the voltage profile that it has seen. It's a two-terminal device, and it gives you a fixed synaptic response for a given device geometry. The advantage, though, of making a synaptic device out of a 2D material is, again, due to the weak electrostatic screening, you can easily gate that memristor device, and therefore make a device that's a hybrid memristor transistor, or we can call that a MEM transistor for short, that's going to allow us to have gate tunability over the synaptic response. And that's going to allow us to gain even greater control in a neuromorphic context. To briefly show what these MEM transistors look like, let's first look at the two-terminal response on the right. You can see in the forward bias condition a strong memristive loop. This is resulting from field-driven defect motion in the channel of the device, which will modulate the doping near the contacts and therefore the amount of current injection in the device. This would be very similar to any other memristor you've seen before. But what's unique about this memristor is that if you now apply a gate voltage, you get dramatic tunability over the response. And in particular, you get a gate tunability in the order of 10 to the 6th, which is now going to have a hybrid memristive response in the two-terminal behavior and a transistor response in the three-terminal behavior. And what that enables is a variety of new opportunities for memristors. For example, if you fashion these dual-gated MEM transistors into crossbar arrays, you can utilize the fact that they're gate tunable to address individual elements in the crossbar without any additional circuit elements required. This is in contrast to memristors, where you typically need a transistor or a diode to do the selection of one element in the crossbar. That, of course, has advantages for higher density crossbar arrays. And while that's an important practical implications, more fundamentally, what the gate tunability of the synaptic response enables is your ability to tune the so-called potentiation and depression response. Potentiation is equivalent to how your synapse learns. Depression is how your synapse forgets. And as a result, you're tuning the learning behavior of your synapse just via the gate you're applying to the device. For example, you can dial in potentiation and depression curves that are optimized for different neural network applications, such as pattern recognition. And if you do this, you can get pattern recognition that now approaches theoretical limits and significantly improves upon what is achievable with conventional memristive crossbar arrays. Okay, let me move on to the final topic, and that is now discussing how we can utilize heterojunctions to add value in energy applications, particularly energy storage, such as lithium-ion batteries. And in that context, a few years ago, we asked the question, is there really an opportunity for solution process nanomaterials in batteries? Could we perhaps use them as the electrodes, either the anode or the cathode? Could we use it as the separator? I already showed you some evidence that indeed you can use it as a separator. Could you perhaps use it as the electrolyte itself? And where I think the greatest opportunity probably is that these so-called SEI layers, or solid electrolyte interphase layers, that build up as you cycle your battery. These SEI layers are relatively poorly controlled in modern lithium-ion battery technology and underlie a lot of the problems that you have with, for example, limited lifetime and safety of lithium-ion battery technology. And as what we decided to target the SEIs first when we introduced 2D materials into battery technology. And in particular, what we wanted to do was think about how we could utilize a material like graphene as an interfacial layer between the electrolyte and the active materials and the electrodes. And the challenge is that a lithium-ion battery electrode is a pretty complicated structure. It's consisting of a large number of particles, conductive additives, and binders. And to get your graphene to coat each and every active material in a conformal manner is a non-trivial process, but one that's enabled by our printable graphene inks. And that ethyl cellulose not only disperses graphene in conventional solvents for lithium-ion battery electrodes, but also the active materials themselves, in this case, lithium manganese oxide. And by controlling the curing conditions, you can now drive that graphene to shrink wrap each and every particle in your composite electrode, giving you now an essentially perfect few layer graphene conformal coating, which now presents a physical barrier between the electrode and the electrolyte. And that physical barrier will now control the SEI and any other unwanted deleterious chemistry that happens at that interface. And in particular for lithium manganese oxide, it famously has a problem that manganese dissolves into the electrolyte upon cycling, which leads to capacity fade, which is amplified in full cell batteries because that manganese not only leaves the cathode, but also diffuses to the anode and compromises its performance. And that's shown in these green curves here in the control, particularly in the full cell on the right. You can see that lithium manganese oxide fades rapidly, and this is why LMO never really made it in most commercial lithium-ion battery contexts. However, if we coat that lithium manganese oxide with graphene, we now see a substantial improvement in cycle life. And this is because the graphene is mitigating the manganese dissolution pathway. I also want to stress, though, that this coating is not only giving you a chemical advantage, but also an electronic property advantage, and that graphene is even more conductive than the traditional carbon black conductive additives in lithium-ion batteries. And as a result, you get a reduction in the impedance of the battery, which allows you to improve the kinetics of cycling. And that's shown in these cycling curves here, where now we're going to change the rate at which we're cycling, where 1C means we're cycling in an hour, 20C means we're cycling in 3 minutes. And in the control in purple, you can see that when you try to cycle a battery faster, you get incomplete charging. And this is, of course, something we all know. If you only charge your iPhone for a few minutes, you get incomplete charging. However, due to the lowering of the impedance from the graphene coating, you can see that even at a 20C rate, charging time of 3 minutes, you get 75% of the capacity preserved. So this has pretty significant implications for high-rate lithium-ion battery technology. But what I want to stress is that in our initial work, we were basically just making a mixture of graphene and the active material. And if you put enough graphene in, you will get a conformal coating, but that means that you also have a lot of excess graphene that's just providing dead weight in the battery. And so the question is there a more clever means by which you could get the graphene to coat only on the surface of the particles in solution? And the way we do that is to use another chemical trick, namely Pickering emulsions. So in a Pickering emulsion, what you have are two immiscible solvents, in this case, hexane and acetonitrile. Because they're immiscible, you'll form an emulsion, but that emulsion is only stabilized if you have a third party present. And that third party is going to be our graphene ethyl cellulose powder. And that will now stabilize the hexane droplets in the acetonitrile external solvent. And by tuning the conditions of your Pickering emulsion, you can control the droplet size. And it turns out that our active material, such as lithium manganese oxide, wants to disperse selectively in the hexane, and as a result, it is recruited to the interior of your hexane droplet. So now what we have are individual droplets of hexane. On the exterior, we have our graphene. In the interior, we have the active material. If you then perform fractional distillation, which will first evaporate the hexane, you get a collapse of the droplets and a collapse of the graphene around your particle. And as a result, now you can get a conformal coating at an order of magnitude less graphene in your final battery electrode. So now at a level of about 0.5 weight percent graphene, we can get essentially perfect coatings over whatever battery cathode you want to use. For example, if you want to use nickel-rich cathode like nickel cobalt aluminum oxide, that works just as well as lithium manganese oxide. And because we've now minimized the dead weight, we get an enhancement of the specific capacity compared to the total electrode mass. And of course, we have less wasted space and therefore higher volumetric capacity, now approaching theoretical limits. I want to note that all this is done in a scalable manner. And as a result, we were able to spin this out of our laboratory into a new company called Valexion, which successfully competed in the Argonne Chain Reaction Innovations Program. And they're now producing these graphene-coated cathodes for a wide variety of lithium-ion battery applications. And incidentally, the same graphene encapsulation scheme works on the anode side as well. For example, in some of these very recently pursued lithium titanium silicon oxide anode materials, you get beautiful graphene coatings. The graphene coatings improve charge transport in your electrodes, which will improve rate performance, as I showed you previously for cathodes. The final frontier would then be the electrolyte itself. Is there an opportunity for 2D materials to do something for the electrolyte? And of course, since 2D materials are solids, presumably that means we need to do a solid electrolyte. And I want to stress that solid electrolytes are highly sought after for lithium-ion battery technology, and that they present safety advantages, better thermal and chemical stability, and easier packaging. And as a result, if you look in the literature, there's a wide variety of materials being pursued for solid electrolytes. Since I don't have much time today, I'm not going to walk you through each of them individually, but what I want to stress is that each of them has some issue which has prevented them from achieving wide-scale adoption commercially. And as a result, I would contend that there is an opportunity for a new type of solid electrolyte. And the one that we are pursuing is to make a so-called ionogel, which is a gel combining ionic liquids, which provide ionic conductivity, with a solid matrix. And in particular, we're pursuing hexagonal boron nitride as a solid matrix for the reasons that we use it in a separator. It's electrically insulating, has high thermal and chemical stability. And if you formulate your ionogel correctly, hexagonal boron nitride will give you a substantial improvement in mechanical integrity, which is the historical issue with gel-based electrolytes. And that's shown here. What I'm plotting is the storage modulus of the ionogel versus the ionic conductivity. Where you want to be is in the upper right-hand corner of this curve, having high mechanical integrity and high ionic conductivity concurrently. And if you look in the previous literature for ionogels, you always saw a trade-off between those parameters. But by using appropriately surface functionalized and exfoliated hexagonal boron nitride, you can enhance the binding to the ionic liquid, and in that way achieve a high storage modulus without compromising ionic conductivity. In addition, that strong interaction between the ionic liquid and the hexagonal boron nitride also enhances the electrochemical stability of your electrolyte, specifically allowing you to go to much higher potentials than you can achieve with the ionic liquid alone. Specifically here, we can see charging and discharging up to 5 volts being stably achieved with these hexagonal boron nitride ionogel electrolytes. And as a result, if you make a battery utilizing an anode like lithium titanium oxide and a cathode like nickel manganese cobalt oxide, you can get very stable solid state batteries with stable charge discharge and high Coulombic efficiencies, and because hexagonal boron nitride is thermally stable, high temperature operation up to 175 degrees Celsius. So that all looks good, but there is one final catch. And the catch is that the ionic liquid that we use in our initial work, TFSI, has a finite electrochemical potential stability window. You can see it goes from about 1 volt to 5 volts, which is why in our first work, we had to use lithium titanium oxide as the anode, because that's a relatively high voltage anode material. But of course, in a real battery, you'd like to use a lower voltage anode like graphite, but that's incompatible with the TFSI. However, if you switch out to FSI, you can get down to the anode low potential, but then you can no longer reach the cathode high potential. And as a result, what you need to produce is a layered heterostructure electrolyte where only the high potential ion gel touches the cathode and only the low potential ion gel touches the anode. And historically, that's been impossible due to too much intermixing at the hetero interface. But due to the strong interaction between the HBN and the ionic liquid, you minimize that intermixing. And as a result, you can now achieve a heterostructured ionogel, which gives you very high stability over the full voltage range of a graphite NMC battery, which gives you high cycling stability. And just incidentally, I should note that if you simply blended the ionic liquids, the performance is terrible. The reason being that you have now each of the ionic liquids touching both electrodes, and as a result, very rapid degradation of their performance. Okay, with that, I'm sure I'm out of time, so I'll conclude there. I tried to make 2 points today. One is that tunable solution rheology has enabled a suite of printable nanomaterial inks compatible with commercializable additive manufacturing. And furthermore, by using these atomically thin materials and heterostructures, you can achieve not only old types of devices, but completely new types of devices, including opportunities in neuromorphic computing and energy storage technologies. With that, I conclude by acknowledging my research group. This is a very recent photo from our lab, which we took before the Delta variant shut us down again. But at least we had a month or two where we could interact in person without masks. Also want to thank the funding agencies for supporting all the work in our laboratory, and finally, thank you for your kind attention.
Thank you, Mark, for the very comprehensive talk, and it shows us how the powerful chemistry processing approaches can help the process of all kinds of nanomaterials and address challenges in electronics, in energy storage. So I guess I have a question. Since you process certainly you pioneered on the carbon nanotube as well as the 2D ink. From the electronic point of view, I'm curious, what's your take on these two types of ink in terms of, for example, for the printable electronics, which one would you say actually have a better potential for the print?
Yeah, if you ask me, just as a thin film transistor, I would say today carbon nanotubes, or I should say specifically semiconductor carbon nanotubes, are still better than any printable 2D semiconductor that I've seen. But if you want to realize a neuromorphic device, and I showed a couple of examples today, we find that the transition metal dichalcogenides have some distinct advantages. So I think like any material, it's unlikely to solve all of the world's problems, but it will be well suited for particular problems. Sure. From our point of view, if you just want to make a TFT, I would use nanotubes, and Nanointegris would be happy to sell them to you, incidentally. But if you want to make a neuromorphic device, I would say the 2D semiconductors have some pretty distinct advantages. Okay, thanks a lot. I guess in that of time, let me see whether there's any question posted or not. Probably in that of time, we'll conclude this session. For now, I will take a probably 8 minutes break. We come back on 10:35.
And I think Professor Paul West is going to chair the next session, and Professor Omar Faha is going to start next session. Thank you, Mark, and thanks to all the speakers in the morning.
Just a heads up that we have a 5-minute delay and it'll be starting at 10:35. So hang in there for 3 great talks in the next session. Okay, I think I'll start my introduction now so that we can give our speakers plenty of time. I'm Paul Weiss at UCLA, and it's my great pleasure to chair the next session. Our first speaker is Omar Farha, who's the Dow Chemical Company professor in chemistry at Northwestern University and an associate editor at ACS Applied Materials and Interfaces. We're proud that he is an alumnus of our chemistry department at UCLA. His research, for which you heard earlier that he's being awarded the Stoddard Prize today, focuses on the rational design of metal organic frameworks for applications in sensing, catalysis, storage, separations, and water purification. He's a fellow of the European Academy of Sciences and the Academy of Arab Scientists. He's won the Kuwait Prize, Japan Society for Coordination Chemistry, International Award for Creative Work, the RSC Environment, Sustainability, and Energy Division Early Career Award, the ACS Satinder Ahuja Award for Young Investigators in Separation Science, and the ENFL Emerging Researcher Award. And there is an award named after him in the chemistry department at Northwestern, the Omar Farha Award for Research Leadership. Omar, welcome and congratulations. Sorry we don't have you here in person. We'll look forward to seeing you talking science and playing together soon. The floor is yours.
Thanks, Paul, and really thank you for the selection committee for this prestigious award. And let me echo what Mark said earlier. This particular award means a lot to have my esteemed colleague's name next to this award. So thank you very much, and I'm very honored. I'm gonna hopefully tell you about some of the work we do in my group. Hopefully I would not use the word I did not do anything. This is the team of the group that actually, it was about a couple weeks before we opened up for Mark to take his beautiful picture with his group. So this is about a 3-month-old picture, but these are the guys who actually do the work. Without the collaborators, and in particular the government and the Army lab collaborators, I wouldn't be able to tell you much about the topic I'm planning to discuss with you today. And without the funding, we wouldn't be talking about that as well. A few years ago, the CNE magazine put a really nice, a whole issue about chemical weapons and starting all the way back to World War I. And you might be asking yourself, why is Omar even starting with that? To hopefully be able to convince you this is a very topical topic. And I'm not going to get into politics. Just go do a quick Google search, and you'll find out a lot of the chemicals that I will be talking about today that we have the ability to go and neutralize have been used in the last 5-6 years illegally. That means we still have to do something about that. And the problem is, how can we win against these toxic chemicals? And before we even do that, we need to understand how these toxic chemicals, they have this particular toxicity. And if you understand that and how they work, you might be able to come up with materials, not just to capture them, but to also neutralize them and degrade them into something either a lot less harmful or non-toxic at all. We all have an enzyme called acetylcholine esterase. Its job to really do the reaction in the bottom. This is an acetylcholine is a neurotransmitter. Once you do a particular job, this enzyme comes and destroy the neurotransmitter for you to stop doing what you're doing. However, in the presence of one of those toxic chemicals, they go and they bind to that triad inside the active site of this enzyme, and they bind irreversibly. With that, you will have no control over your breathing, over your muscles, and that leads to a lot of bad things. And as you could see from this picture, finding protection group for the soldiers, even civilians or the animals, is not anything new. The question is, I would argue that the technology did not keep up with these new chemicals and these new agents because we're still using similar technology as it was used 50 years ago, a little bit of oxides sprinkled inside activated carbon, and they have no catalytic efficiency. It's mainly capture and hope that you're not filling your canister before it diffuses. Another thing you could see, these toxic chemicals are really easy to make. That's why you could people are finding plenty of them everywhere around the world. The next thing is, if we want to go after such toxic chemicals, can we really come up with a platform technology that has the ability, if we find a warehouse that we need to get rid of in an environmentally efficient way, we could do that. But at the same time, we're not really changing everything and starting from scratch if we want to put it inside a mask or a filter, or even coat the whole entire suit or uniform that either a soldier will wear, or even some toxic chemicals used, such as insecticides or pesticides by farmers, all the way to having an antidote if somebody really gets these toxic chemicals into their blood and body. And from the title of my talk, you know that I'm going to talk about metal organic frameworks. We just heard a beautiful lecture by Professor Yagi. Just allow me 1 minute to put my perspective here. We build them from metal ions and metal clusters, organic linkers. We make two-dimensional, three-dimensional materials. I personally got into this area because you have a periodic table to pick from, and you have hundreds and thousands of organic linkers with a lot of connectivities to pick from. These materials are really, you could think, because of the self-assembly and the complementary reactivity, you could think about them as programmable. And if they are programmable, that means they should be scalable. And hopefully I'll be able to show you at the end of my talk that the scalability of these materials now, it can be done, and it can be done easily. But at the same time, because you have that many metals and that many organic linkers, then you have hundreds of thousands and millions options to build these materials with different morphologies, topologies, chemical properties, physical properties, and sometimes you get a lot of these beautiful structures, and that's why modeling and computing has flourished in this area, because the experimentalists are able to make a lot of these materials as crystalline, get the crystal structure, and know where everything is down to the atomic level. There is no university should be able to allow you to use these toxic chemicals, and that's why in my lab we use what we call surrogates or simulants. That means these molecules, they mimic the reactivity of those agents, but they are not toxic the way the agents are toxic. And at the same time, once we have a good catalyst and a good material, we collaborate with the Army labs and we ship it to them. We want to do this catalysis in a very simple way. Simple, but it's actually hard to do. We want to be able to hydrolyze that PF bond, that very reactive bond, and make it into a POH bond, which is a lot less reactive, and we want to do it with just water. You know, nature actually figured that out very early on, and nature does it really well. Except nature, the enzymes and the proteins that has ability to do such a transformation are not stable under the environmental conditions we want to use it under. If I was giving a different talk how we stabilize enzyme, I would have told you what we could do to stabilize those enzymes. But today, let's be inspired by these enzymes, by these, how they work and why they work, and what's the active site looks like. This particular enzyme has an active site that has 2 zincs bridged by hydroxyl. You have some histidines, those are the bases, and some carboxylic acids. And this is the mechanism. The main important point that the zinc here plays as a Lewis acid for the simulant or the agent to bind, or a hydroxyl group to attack, and then you could regenerate the active site and you go on. When we started this work, zinc-based MOFs weren't stable enough. Zirconium-based MOF were very stable. But if we're talking about really Lewis acidity, is that what we need here? Zirconium MOFs are, or zirconium +4 is actually a better Lewis acid than the zinc moss. So this is a small piece of a zirconium node, and I will show you the whole thing in a second. Well, you could see you have two zirconiums bridged by hydroxyls, carboxylic acids. Is not far away. I'm not saying here we're trying to mimic the active site. We just need to be inspired by the active sites. This is the whole cluster. It's 6 zirconiums, so you could think about it as a small piece of zirconia, nano zirconia. However, it's capped by 12 carboxylic acids, and later on that becomes important. So every time I use the word connectivity, 12 connected, that means you have 12 carboxylic acids around the zirconium 6. If I say 10 connected, that means it's still zirconium 6 node, but now I have only 10 carboxylic acids. So what happens to the other two? We replace them with water and hydroxyls for each one to balance the charge. This material, it was made in almost 2008, called UIO66. It's based on University of Oslo, and it's a very stable. It's made from benzene dicarboxylic acid, which is the main ingredient for the plastic bottles. So you could see this is a linker that has been scaled to hundreds of thousands of metric tons. Zirconium, Omar was saying it's expensive. It's expensive if you want to use it for water capture, but if you need to use it as a protection in suits and masks, it's not very expensive to save somebody's life. And at the same time, these connectivities are very stable, and that's why we went after this chemistry. So this is the reaction that we want to do. So you have the simulant. We want to use a catalyst. We want to use water. We want to use a base because you got to form some acid to neutralize it. And we want to monitor the appearance of these starting materials or the nitrophenol. There is issues with this reaction. This reaction is good for screening because, first of all, we are using bulk water. If you want to put it in a mask, there is no bulk water there. And second, we are using ethylmorpholine, but this is a volatile base. And hopefully by the end of my talk, I will show you how we were able to handle both of those issues and actually get our materials to be very close to be implemented. Here, the reaction, you could monitor the reaction by two ways: the UV vis, seeing the disappearance of the starting materials of the appearance of the product. If you don't have a UV vis, you could follow using the phosphorus NMR, and once again, you could see the disappearance of the starting material, the appearance of the product. The main thing, and ignore which catalyst is this, you will see that in a couple slides. Regardless which technique you use, you get to the same answer. So that's good. So now we did this catalysis with the UIO66, our first generation catalyst, and we got a very selective catalysis based on the phosphorus NMR, which is great. And we got a conversion or a half-life of about 50 minutes at room temperature. Let me spend 30 seconds here. So why are we using half-lives? Because the Army labs wants everybody to use the same exact conditions, regardless where you are in the world, and they use half-lives instead of turnover frequencies or turnover numbers. Half-life is how much chemical did you convert to a product in how many minutes or how many hours or how many days to convert half of those amount of chemicals into that product. This is actually was interesting. Why? Because before this, we had different complex materials that we worked really hard on, and it was 36 hours half-life, which I'm not going to talk about that. So when we got a 50-minute half-life at room temperature, we didn't have to heat our reaction. That was very exciting. But we also characterize our catalyst before, after, to make sure we're really not fooling ourselves and doing heterogeneous catalysis. And we use every technique available to us to confirm that our catalyst stays intact based on mass balance, filtration test, isotherms, PXRD, you name it, we do it. So take my word for it. When we send this material to the Army labs, the half-lives it was 10 minutes instead of 50 minutes. And that's actually not surprising. The reason for that, the simulant we use, it's more stable because that's why it's less toxic, which means it's harder to destroy. That's what you want to be. You want to be using a simulant that is harder to destroy. This way, when you ship your samples, to your actual, to the Army labs, they should be able to do better with the agent than what we did with the simulant. So far, this is good, but the question is, can we do better? I told you that we started with this 12 connected. Everything is coordinating. That means some bonds have to break, some bonds have to form. But how about if we have less connectivity? That means we have less carboxylic acids. For every carboxylic acid is missing, we could put, we balance it with a water and hydroxyl. That means those catalyst sites are more accessible. And the question is, if that's more accessible and we don't have to make and break bonds as much as in a 12 connected, can we do better catalysis? So to look at zirconium-6, because we want to maintain that, if you look at it from a geometric point of view, we could really build things all the way from 12 connected, all the way to 4 connected and anything in between. If you put it in a chemical sense, that's how we build them. These are the SPUs, and they look, you could see if it's a 4 connected, it looks like a square. If it's a 12 connected, it looks like a polyhedron. But here you still have the zirconium-6 cluster. That's the good thing. We make those, we force those nodes to be whichever connectivity we want based on the linker, and we have the linker direct that chemistry. And these are the linker we typically use a lot, some simple, some more complex, but we force them. And we wanted to start to go from the 12 connected to the 8 connected. And the way to do that, you just use a cube and you use a square. I could give a whole lecture on that, so take my word for it. You will make this particular, at least in a PowerPoint presentation, you should make this topology. And if you go to the lab and you mix those two together, and if your students is patient enough, they will make the right thing. And after you make it, you could really scale it up. At least in my lab, we could make 10 grams easily in one batch and have 100 grams of this linker very easily. And you could actually get the crystal structure of this material, and you could see down to the atomic level, did you make what you wanted to make or not? This material is quite stable from different pHs. It's very porous, and this is the nitrogen isotherm. For the people who are not familiar with nitrogen isotherm, this is the uptake of nitrogen at 77 K with respect to pressure, and you could see that regardless what you do to it, it does not change. So that's good. Now let's do the catalysis. Did it do better than our Gen 1 material? And the answer is yes. We went from 50-minute half-life to now 15-minute half-life. So at least our hypothesis was correct, and we were going in the right direction. And when we send it to the Army labs, now they get 2-minute half-life instead of the 10-minute half-life with the original Gen 1 material. The nice thing is, a couple of years ago, another team from Virginia Tech, they were able to take our material and go to the synchrotron and do in situ catalysis, and they showed that our mechanism and where we are proposing the catalysis taking place on that zirconium node is actually correct. It's nice to see that different teams can find exactly what you propose. So now, if 8 connected is good, can we go to lower connectivity? So we're into the 6 connected. This is a MOF called MOF 828. It has 6 carboxylic acids, and the other 6 are replaced by waters and hydroxyls. This material is quite beautiful. Here, even at half the loading of the catalyst, our first data point, we get complete conversion of the substrate. So we know the half-life of the simulant, not the agent itself, is really less than a minute. But let me remind you, everything here is done in liquid water with a volatile base. So this is condensed phase reaction. Just to summarize this part, so this is 3 generations of a catalyst going from 50-minute half-life, 15-minute half-life or so, all the way to getting less than a minute half-life. So now we need to address that problem. We have this volatile base, and we have this liquid phase water. The first one, can we heterogenize this base? And the answer is yes. We start thinking about that. If amine, a secondary and tertiary amine is all what we need, then can we use linear and branch polymers to use as bases, and those are heterogeneous at the same time. So now we tested these in replacement of the volatile base, and it works just as well as the volatile base. So that's the good news. The next thing is, if we want to put it in a suit, now we need to be able to put these materials into the textile in a way that these things not gonna fall off real easily. And the idea is here, right now, some of the suits for the Army, they have a layer of activated carbon. We want to replace that layer of activated carbon with a layer of our material, because the activated carbon, the only thing it does is soaks up the agent, it doesn't destroy it. Versus our material, the sponges, they have the ability to soak up and deactivate at the same time. And that's why the Department of Defense is really intrigued about this technology. So how can we now put MOFs on these textiles in a scalable, easy manner? So if we do that, we have three things we need to worry about. The first thing is being able to find the right MOF. I showed you, I hope we did. Being able to heterogenize the base. I showed you that we just did that. The last thing that we had to address, we cannot use just condensed beaker of water. Can we rely on the humidity and use that water in the humidity as the source of water to do this catalysis? And Omar showed us that MOFs have the capability of capturing water even in the desert. That's nice. That means there is a MOF there to be able to capture enough water from humidity, regardless if you are at 50% relative humidity or in a desert down to a 10% relative humidity. Let's stick with the MOF that I showed you that has really good catalytic activity, MOF A28. If you do the water isotherm of MOF A28, you'll find out anywhere above 15–20% relative humidity, these cavities are filled with water. That means really there is no good reason to use a beaker of water if the reaction is happening inside those cavities, because you have plenty of water to do your reaction. And we do our reaction in a controlled manner in order to control our humidity precisely. Now, we know which MOF that capture water from your humidity, and we don't need a beaker. The second thing, we know how to heterogenize our base with a polymer. And the polymer, we want it to act as a glue when we start taking them off and coating it on these fibers. And we came up with a dip coating technique, very similar to how the denim industry really coat the jeans with a lot of coating processing. So this is really roll to roll. We could make a meter of that very easily in my group. So you could see that in a textile company, they should be able to scale up this particular technology. Now everything in the solid state. And when we do this reaction, it works beautifully in the solid state. There is no volatile base. There is no condensed phase water. And when we send it to the Army, again, it works also beautifully against the agent. One thing you should see that we went from about a minute, 2-minute half-lives to 12-minute half-life with the solid state, taking it out from doing condensed phase reaction. And that should be fine, but we wanted to push the boundaries and see, can we do better? One way to do better is to take our polymer and actually make them into a hydrogel by cross-linking them. Why is that important? If you do that, then you should be able to invite more water into the reaction media close by the active site. And can that accelerate the reaction? It's a very simple chemistry, very well understood chemistry, how you take the branched PEI and make it into the hydrogel. Then we mix it with our MOF. We maintain porosity, we maintain crystallinity. And this material, even if before we even put it on the textile, it's white. And the simulant itself is clear. The color comes from the product. And you could see, really, as soon as we drip that reagent on our hydrogel, it starts to degrade in it immediately. That's good news. Now we take this material and we coat our textile and our fiber with it, maintain the crystallinity and the porosity, and now we get half-lives or reactivity very similar, almost identical to what we get in condensed phase fashion. So this is actually quite nice to get to this point. It took us about 8 years to get to this point, but what do you do from now? There is a big contract was given to a startup company called Numat Technology in jointly with the Revolution Pipers from New Zealand and Patagonia. A lot of us most likely wear their gear now to make hundreds of suits very soon to be deployed and tested in the field. So Numat Technology is a startup company that I started in 2014. It has right now, actually, as of a couple of weeks ago, 45 full-time employees. This company, it goes from all the way from computational driven discovery to always to a product launch. We could make things at milligram and gram scale, kilos, and we have our own pilot plant facilities that we could make hundreds of kilos to metric ton and anything in between. So this is just some of the materials we make. So our first product actually was in the semiconductor industry. We were able to make sponges that we could store them in cylinders to be able to soak up and release very toxic gases for the electronic industry, such as BF3, arsine, and phosphine. But instead of using it at high pressure, we fill those cylinders subatmospherically. You get more than the high pressure cylinders, except you do it at subatmospherically for safety. This is the product is called IonX, and it's been sold worldwide for the last few years. It's been tested by third parties, instrument makers, chip makers, and they've been writing some nice reports about the product and how it behaves. Merck Germany is our actually partner for distributing these product, filling and distributing these product worldwide. And our Asia filling facility, thank goodness, was built and finished before COVID and stayed operational during COVID to actually take care of the customers as needed. With that, I would like to thank you again for listening to me, and thank you for the award as well. And hopefully I was able to get us back into a few minutes instead of staying behind.
Very much so. Thank you so much. And we do have time for questions. Those can go in the chat, or you can simply unmute yourself if you would like to ask one. Maybe I'll start. So one of your specialties has really been design of these materials. And so when you're looking for the next generation, what is it you'd like to have and to include in them?
No, I mean, the next generation is we're already working on. So if you looked at that enzyme, it has those histidines. And those histidines are not just randomly placed next to an active site of an enzyme. They actually shuttle protons between the active site and the catalyst, and making the catalysis and regeneration of the catalysis much better to give you a lot more turnover numbers. And that's what we're actually doing right now. We are placing those histidines on our organic linkers to be very close to that active site to hopefully start getting closer and closer to how the enzyme work. Second thing is, if zinc is what the enzyme uses, it doesn't use zirconium. When we started with zirconium, because there were no zinc stable muffs. 10 years later, now we could make very stable zinc muffs. So now we're starting to implement zinc muffs because they are a lot cheaper, but at the same time, we're getting also, as I said, nature used zinc for a good reason. So now we want to see if we use the histidines in the world and the zinc, can we make our Gen 4 material to even be better than our Gen 3 material?
Interesting. Yeah. And maybe one more while we're, yeah. So you have these companies you're running and sort of overlapping science with your lab. How do you manage that and your time?
The good news is you hire people who are smarter than you. So that's why I have a, you know, VP of marketing, VP of sales, and you have a CEO, and you have 45 employees from business to engineers to chemists to do everything. That means now it's on a cruise control. I don't have to be micromanaging the company.
Yes, very good. Well, if there are not further questions, let's thank Professor Farha again, and congratulations again on the award. We'll look forward to having you here, hopefully at the next one of these meetings, and to seeing you in person before then. Thanks again.
Paul. Appreciate it.
Very good. So our next awardee lecturer is Professor Andrea Alu. He's the founding director at the Photonics Initiative, Advanced Science Research Center, and the Einstein Professor of Physics at the Graduate Center of the City University of New York. He's a fellow of the National Academy of Inventors, the MRS, the AAAS, the IEEE, the Optical Society of America, SPIE, and the APS. He's received the Dan Maiden Prize in Nanoscience, the IEEE Kiyo Tomiyasu Award, the Vannevar Bush Faculty Fellowship, the ICO Prize in Optics, the Waterman Award from the NSF, the OSA Adolf Lamm Medal, among others. We now proudly add the AAAFM Heger Award to this long list. And let me turn the floor over to you, Professor Ali. And you can go ahead and you should be able to share your screen now.
Thank you, Professor Weiss, and thanks the award committee for this recognition. I'm honored and humbled to receive it. I'm sorry we cannot do this in person, but I'm glad to discuss a little bit of our recent results in the context of manipulating and tailoring light at the nanoscale using polaritons and metamaterials. So part of my work is in the area of nanophotonics and realizing structures and circuits that can manipulate light at the nanoscale and realize multiple functionalities. These opportunities arise from the fact that we can use nanostructured materials that can confine light at the nanoscale and can enhance the typically weak interactions between light and matter. However, typically this comes at a price because light does not like to be squeezed beyond the diffraction limit, beyond a few hundred of nanometers. And typically this implies, therefore, the need for large quality factors, narrow bandwidths of operation, enhanced sensitivity to losses, and oftentimes large footprint requirements. These limitations draw to fundamental electromagnetics principles. Passivity, causality, non-locality all play a role in how much we can actually squeeze light and take advantage of small volumes and enhance the local density of states. For this reason, lately we have been interested in exploring new material platforms that combine or strongly couple oscillations of light with matter. And this allows us to overcome some of these trade-offs. This comes in the context of polaritons that are a strong coupling between photons and material excitations that can come in different forms. We have been using, for instance, electron-hole pairs in semiconductors, intersub-band excitations, excitons into the materials, electrons at the surface of metals, phonons, and optomechanical phenomena, magnons, and several other material excitations that, when coupled strongly with light, enable new form of excitation known as polaritons that can overcome some of these limits, especially when these are combined with the proper nanostructuring of these materials. So in the past few years, we have been looking at ways of combining several material platforms, transition metal dichalcogenides, oxides, multiple quantum wells, graphene, boron nitride, calcite, beta-gallium oxide, exploiting the underlying lattice symmetries in these materials, the thin form factors, and the phenomena, physical phenomena that happen at the nanoscale in these materials, combined with metallic materials and structures to enable new optical phenomena and emerging features that do not are not available in the unstructured materials themselves. I will give a few examples of how these polaritonic metamaterials, metasurfaces, can help advance the field of nanophotonics. A first example is the concept of nonlinear optics. If we take a conventional nonlinear material like an optical crystal and we study its nonlinear optical responses, we find that typically they are perturbative. The linear responses have, let's say, order 1. The nonlinear phenomena, so the mixing of more than one excitation and the resulting nonlinear polarization induced in these materials, typically comes at an order, several orders of magnitude less. This implies that to really observe this phenomena, we need extremely large intensities if we're limited to the nanoscale. That's why the traditional approach to enable nonlinear operations with in optical devices is to stack over large footprints several of these nonlinear materials and carefully tailor engineer the structures such that we can coherently sum these small effects until we get actually a sensible, non-negligible response. Conversely, what I'm going to show you is that by combining strongly nonlinear materials with tailored nanostructures, it's possible to come up with a new paradigm for nonlinear optics that does not require phase matching, happens at the nanoscale, and can result in orders of magnitude enhancement in localized nonlinear response. One approach we have been using in this context is to tailor end-doped multiple quantum wells that are known to support very large nonlinear responses associated with intersub-band transitions in the mid-infrared wavelength range, and then combine this with suitably tailored nanostructures, in this case gold nanoantennas, whose shape has the role of enhancing the electromagnetic fields at the desired frequencies that we want to mix, and also convert impinging polarizations that can be arbitrarily oriented with the desired polarizations, typically vertically oriented with respect to the layers of these multiple quantum wells that are associated with the intersub-band transitions in the materials. This results in strong polaritonic responses that can realize orders of magnitude larger nonlinear phenomena compared to the conventional phenomena we can find in an optical crystal at these frequencies. This was our first demonstration in collaboration with Misha Belkin. At the time, both our groups were at UT Austin, in which we realized a metasurface a few hundred nanometers thick that showed a giant nonlinear optical response at 8 micron wavelength. This was tailored for second harmonic generation. So the structures were designed to also strongly engage light at 4 micron wavelength at the double frequency to enable large efficiency in harmonic conversion for these structures. These are later metasurfaces in which we actually etched out material. So interestingly here, we are removing nonlinear material, but confining the fields more strongly around the gold nanostructures. We were able to further enhance the response and enable more efficient nonlinear optical conversion. And these are the latest structures we've been working on in realizing optimized intersub-band transitions coupled to strongly resonant gold nanoantennas that can overcome some of the usual trade-offs in nonlinear optics. The idea here is to go into a flatland structure in which each deeply subwavelength element can realize efficient frequency manipulation and nonlinear operations on the impinging light independent of the surrounding pixels. So really extending the concept of a metasurface in which subwavelength elements can independently control the impinging light to nonlinear responses. An example moving in that direction is this idea here in which we exploit geometrical rotations of pixels that are individually optimized to enhance the nonlinear response, and we exploit the geometrical rotation to add phase to the outgoing circularly polarized second harmonic frequency. Prove that a rotation in the pixel corresponds to a phase added to the nonlinearly generated light, and this implies that by tailoring and patterning the rotation on this surface, we can actually control the or pattern the phase front of the nonlinearly generated beam. These are some examples of metasurfaces in which we are tailoring the gradient with which we rotate these nanostructures, and these are the corresponding optical beams as they emerge from the surface. In all these experiments, we are illuminating the surface at normal incidence with a uniform field, but the second harmonic generation comes out at an angle that depends on the gradient with which we tailor this rotation along the surface. We have also looked at more sophisticated patterns in which we can do, for instance, focusing of this impinging, of these emerging nonlinear wavefronts. As another example, we've been looking at ways to realizing more efficient reflective limiters. A reflective limiter is a structure that for large densities absorbs the impinging radiation, but for low intensities actually reflects. And this typically can be achieved only with large footprints or with narrow bandwidths and large field intensities, field enhancements coming from the optical nonlinearities. The alternative that we've been exploiting is again to look at the combination of nonlinear responses in these multi-quantum well structures combined with gold nanostructures on top that are tailored to enhance this response and basically tune the structure for low intensities to two split peaks that come from the strong coupling between the material resonance and the gold electromagnetic resonance of the optical structure, and poorly coupled resonances in which we have just a large absorbing peak for large intensity. Essentially, the intensity of light through the nonlinearity detunes this strong coupling and this polaritonic response. What's interesting is that this response is extremely fast because we're essentially depleting the population of electrons from the lower to the upper state of this multiple quantum well, and that enables a very fast nonlinearity and a strong nonlinear response at low intensities. These are the material structures that, when illuminated at low intensities, do show this splitting that allows us to observe a large reflectivity in the middle of this gap. And then as we pump more intensity, this detuning, this splitting is detuned, and we get large absorption. And these are indeed the experiments confirming this response. Still, this is not optimal, and we have some recipes to enhance further the contrast between the two states. But the nice features here by measuring the response of this nonlinear metasurface is that the response is very fast. It's in the range of a couple of picoseconds, and the nonlinearity response is extremely large at these mid-infrared frequencies. As another example of the role of polaritons in manipulating nanoscale light, I want to show you briefly the opportunities that come from exploiting the extreme asymmetries in these polaritonic metasurfaces. If we excite with a small emitter an isotropic, a symmetric surface, we expect to induce on the surface a circular wavefront to emit light in all directions with the same features. In some ways, this is similar to throwing a small droplet in a pond and observe the circular wavefronts coming out of the point of impact. If we do a Fourier transform of the emitted optical fields, we find a circular isofrequency contour in momentum space. This is the momentum in different directions on the surface, and the Fourier spectrum in space of this emission indeed results in a symmetric pattern. If we break symmetry and make this surface asymmetric, we will find the preferred directions in which the optical emitter will couple energy into, and but typically to have the same sign. Something more interesting and appealing happens when actually the two responses are largely asymmetric, and therefore the metasurface impedance actually have opposite signs. In this case, the emission from the surface assumes a completely different topology. From being a closed contour in momentum space, becomes an open contour, an hyperbolic response. And this happens when the material response is inductive or metallic, essentially, for electric fields polarized in one direction, but capacitive or insulating for electric fields in the orthogonal direction. Under this condition, the optical emitter will emit preferentially in certain directions along the surface without with a much more collimated beam. A particularly interesting regime comes at the transition from a closed to an open surface. That is when one of the two elements of the metasurface goes close to zero for the conductivity response. In this case, the response becomes flat and induces what is known as a canalization regime, for which all the emitted energy is actually channeled along just a specific direction. This also implies the maximum light-matter interaction coupling, maximum local density of states for the optical modes that we can excite on this surface. So this is particularly interesting to engage the surface with localized emitters. To demonstrate this phenomena, we can again turn into polaritons. In particular, this implementation was realized using boron nitride that at mid-infrared wavelengths supports phonon resonance, for which one of the permittivity tensor elements becomes negative while the others stay positive. And in this regime, indeed, we find that boron nitride on its own supports volumetric hyperbolic modes. To turn these volumetric bulk modes into surface modes, we actually realize a largely asymmetric metasurface through these nanoribbons, this patterned metasurface of boron nitride. And in this way, electric fields parallel to the ribbons feel an inductive response because of the negative permittivity of the boron nitride, whereas the electric field orthogonal to the ribbons feels a capacitive response coming from the gaps between these ribbons. This in turn realizes experimentally this response of canalization at the regime in which the boron nitride supports the phonon resonance. We launch these polaritons through gold nanostructure here, and we observe this canalization of the polaritons just travel in one direction without diffraction. You also observe how they rapidly get damped, and this is because of we're working at the phonon resonance of the material. I will show in a moment how we can exploit slightly more complicated structures to actually get rid of this trade-off between canalization of the polaritons and enhance the loss in the material. Before I do that, I want to show you another interesting example of exploiting these hyperbolic responses in the context of coupling hyperbolic metasurfaces with transition metal dechalcogenides. In this case, we're working with MOS2 that supports, because of its lattice symmetries, an exciton resonance in the visible range that is associated with the K and K prime points of its reciprocal lattice. What's interesting is that these two exciton resonances are associated with specific valley. So they couple with light with a certain handedness. And one of the visions for these materials is to use them to exploit the valley degree of freedom as a form of a bit of information in the context of what is known as valleytronics, in which this opposite handedness may be used as a low energy information platform to route and transport bits of information and process them across a 2D material platform. In order to enable this vision, we've been looking at ways of coupling the MOS2, these transition metal dechalcogenides, with the hyperbolic metasurfaces. The idea is that the hyperbolic responses I just showed you can realize non-diffractive transport of this exciton coupled to light, and at the same time enhance it, so realize strong excitation and coupling of these structures to the surface, and then routing them around the metasurface. The idea was also to exploit this to actually sort different handedness, different excitons towards different directions. However, if we use the same trick I showed you before of these nanoribbons or groove surfaces, in this case, we turn to silver because silver supports plasmonic resonances in the visible. Boron nitride would not work because its resonance, its phonon resonance is in the mid-infrared, very far from the exciton resonance of these materials. But plasmonic responses can help realize this hyperbolic transport at in the visible regime. The unfortunate issue here is that a symmetric metasurface like these nanogrooves would not be able to distinguish opposite handedness because the 2D nature of the material coupled to the surface does not allow to differentiate the different handedness. They must respond with the same strength. However, if we study slanted structures that add a degree of non-locality to this response, we are able to observe this sorting of valley polaritons that are coupled to different directions for opposite handedness. We've been able to observe this. These are experiments in collaboration with Elaine Lee, also at UT Austin, showing how indeed we can discriminate both in the near field and in the far field through dark field microscopy the response of this hybrid metasurface as a function of the handedness. Here we not only enhance the response to the hyperbolic response, but also are able to sort the different valleys as a function of the excitation handedness. A new degree of freedom that can be used to further enhance these responses is the twist angle between two metasurfaces stacked on top of each other. This paradigm has been introduced in the concept of the conductivity response of materials, and in particular, the discovery that a graphene bilayer in which one layer is rotated or twisted with respect to the other at a specific angle realizes this moire pattern for the two crystal lattices that introduces a totally new form of conductivity compared to the individual monolayers. In particular, the bilayer for a specific angle of 1.1 degrees between the two monolayers realizes these flat bands in the conductivity response in the electron energy momentum space introduces superconductivity. We've been interested in exploring if similar responses can be achieved for light, for photons in our metasurfaces, and hyperbolic responses help with that because they provide extreme asymmetry at the level of the single surface. So the idea here is to couple two of such surfaces. Here again, I'm showing a surface of nanoribbons that realizes an hyperbolic response. And then we can stack a second metasurface at a small distance to enable strong coupling between the two polaritonic responses. And by rotating one with respect to the other, we can study whether we can observe emerging features that will not be present without the rotation and coupling of the two surfaces. Interestingly, the problem can be modeled quite accurately by simply studying the response of the individual structures and rotating them in momentum space. Here you see the response of the bilayer, the twisted bilayer, that are the different colored lines, and the responses of the individual monolayers rotated with each other. As you see, the response of the bilayer can be simply predicted by considering that the two the response of the two monolayers induce this strong coupling at the intersection points and realize this avoided crossing at the intersection points. What this implies is that if we study, for instance, a 90-degree rotation between the two surfaces, so essentially the bilayer corresponds to two lattices of nanoribbons on top of each other but orthogonal to each other, the response of the two monolayers has 4 intersection points, and thanks to avoided crossing, the bilayer response turns out to be a closed contour in the center. So quite interestingly, despite the fact that the two surfaces separately support an hyperbolic response, the bilayer actually has a closed contour and an elliptical or a circular response. As we rotate one of the layers with respect to the other, the intersection points actually move. And specifically, if we go down to 30 degrees, so one of the layers is a 30-degree rotation from the other, there are only 2 intersection points. And therefore, the response of the bilayer becomes hyperbolic. So quite interestingly, at fixed frequency, we can largely manipulate the response of the bilayer by simply rotating one with respect to the other. And there is a specific angle for which 2 of the intersection points lie at infinity, for which the band structure becomes flat. That reminds us of the superconductivity regime, but here it corresponds to the photonic response of these materials, or the polaritonic response. Interestingly, compared to the electronic response, here we have another degree of freedom, that is the frequency. In fact, the frequency of excitation changes the open angle of the hyperbolas, and therefore also controls the number of intersection points. And therefore, we can generate this contour map in which by changing the frequency of operation and the rotation angle, we can actually create a map in which we move from elliptical responses to hyperbolic responses through a topological transition here, in which we must expect canalization of polaritons on the bilayer. Interestingly, these features can be observed in natural material in molybdenum trioxide in the mid-infrared wavelength range. Molybdenum trioxide is a transition metal oxide that naturally supports largely anisotropic response on the surface, for which, because supports different phonon resonances for different orientations of the electric field on the surface. So interestingly, it was discovered a couple of years ago that it supports naturally this form of hyperbolic polaritons, phonon polaritons, without any structuring, without the need for a nanoribbon patterning of the surface. This is particularly interesting because by simply stacking two of these layers on top of each other without any rotation, we can actually achieve this response. Here, first, I show you the nanocavity response of a single layer of molybdenum trioxide, in which you see how the rotation of these cavity shapes with respect to the optical axis of the oxide can realize very different resonant profiles, really showing this extreme anisotropy of the optical response. And here I show you these twisted bilayers of molybdenum trioxide. We can see indeed how this response is expected to provide a topological transition at a fixed frequency as we change the rotation angle between the two. This is basically the same map I showed you before, but now calculated for the properties, optical properties of molybdenum trioxide. These are full wave simulations of an optical emitter sitting on top of the bilayer as we change the rotation angle. At fixed frequency, we see a drastic change in the emission response on the surface. And these are Fourier transforms that confirm our analytical predictions when we compare them with the individual monolayer responses. And these are experiments verifying these predictions and showing the, extreme manipulation of nanoscale light using this twisting of molybdenum trioxide bilayers. We first start from a single layer and we verify the presence of these hyperbolic wavefronts in unpatterned molybdenum trioxide. And when we stack two of them on top of each other as a function of the rotation angle, we can observe hyperbolic wavefronts, canalization wavefronts, and elliptical wavefronts at the same frequency of excitation. So the rotation of one with respect to the other and to their optical axis can largely manipulate the optical response of these bilayers. And interestingly, for all these samples, by tuning frequency, we can track the magic angle at which canalization is observed. And therefore, as I promised a few slides ago, we are able to decouple the response from the material resonance and the canalization condition. The best evidence of how we can manipulate and tailor light at the nanoscale is in this plot here, in which we carved the slits on this bilayer, and we're able to observe at the canalization frequency that corresponds to these flat bands in the momentum space. We can image without diffraction these slits independent of their orientation with respect to the optical axis. In each case, we see the projection of the slit towards the only direction towards which polaritons can propagate, and the polaritons travel without diffraction, imaging these slits and with a longer propagation length compared to what a monolayer of molybdenum trioxide could support at the canalization frequency. Things can get even more interesting if we study other common materials as they support hyperbolic polaritons. This is a result that just came out yesterday in print, The idea is to use calcite, that is another material that supports naturally anisotropic phonon resonances in the mid-infrared range. And here, calcite allows us to actually realize an interface, a surface, that is not aligned with the optical axis. This was not possible with molybdenum trioxide because of the nature of the material, but with calcite, we can actually choose to cut the material at an angle with respect to the optical axis. And this results into a new form of polaritons that were predicted in the context of anisotropic materials. They were named ghost waves. These are the first observation of ghost phonon polaritons. They have a very unusual property of being guided at the interface with air, but also have a oblique wavefront in which there is a phase propagation within the material. They're not conventional surface waves, but have these tails that enter the material. And indeed, we can observe these tilted hyperbolic phase fronts when we study the response in momentum space in the reciprocal space over a broad range of frequencies around the phonon resonance of this material. These are again a nanoscale observation of these structures in which we can observe the excitation of these hyperbolic ghost polaritons. We can tune the open angle of these polaritons with frequency, and we have a nice prediction of the open angle. So there is a nice tunability of the dispersion. And in fact, we can even observe nanoscale imaging thanks to this hyperbolic response, and a topological transition that now, rather than being tuned through the rotation of one layer with respect to another, is tuned by cutting the surface of calcite with respect to the optical axis. And you see that different cuts will generate different open angles at the same frequency for the response of these ghost polaritons. Finally, very recent work here in which we made things even more complicated. With calcite, we still obey a symmetry in the excitation of these hyperbolic polaritons because of the symmetries in the permittivity tensor of calcite. But if we look at beta gallium oxide, monoclinic crystal, there is an additional phonon resonance that is actually tilted, slanted with respect to the one that drives the hyperbolic response. And therefore, this permittivity tensor cannot be diagonalized, and the result is in presence of loss, this asymmetric propagation of hyperbolic polaritons that prefer certain regions with respect to others, in which loss coupled differently to different directions because of this additional resonance that cannot be diagonalized in the material. And we've been able to observe this also with both far field and near field measurements, and really exploit the low symmetry of this material to observe hyperbolic phonon polaritons with these unusual asymmetric responses. The final result I want to briefly show you is associated with, to highlight, by the way, the relevance of polaritonic responses to manipulate nanoscale light, is the coupling of phonon polariton, in this case again boron nitride, as I showed you before, but now with a more complicated nanostructure. In this case is an Archimedean spiral with, in this case, 4 arms. What we do here is to exploit the highly confined polaritonic modes in boron nitride and their interaction with this nanostructure with the suitable shape to realize a vortex of polaritons that converges toward the center of the spiral and realize a topological charge in the center of this spiral with different charge as a function of the input excitation. So a reconfigurable topological charge. Let me show you what we mean here. These are near field images of the response of this structure as we tune the excitation the excitation handedness. So by changing the polarization of input light from right-handed to left-handed, we get different responses at the center of the structure. We observe these spiral-like polaritons converging toward the center, and the charge they carry depends on the spin of the input far-field light that excites them. We can use, again, geometrical considerations, as we did before, to calculate what type of topological charge we expect. And in general, the total topological charge will be given by this simple formula, in which m is the number of arms of the nanostructure we use to launch the polaritons. L is the topological charge that depends on the size of the structure and on the wavelength of the polaritons that are excited at the structure. S prime is the polariton mode index, is basically the waveguide mode we use. The thickness of the substrate controls this number. And sigma is the input spin, so the polarization of the input wave. These, for instance, are demonstrations of reconfigurable topological charges at the center of the structures. We go from 0 to 1 to 2 to 3 as a function of the geometry of the structures. We go from 1 arm to 2 arms, and the input polarization. And this one is by simply tuning the frequency, we go to a different orbital charge for the structure, because the wavelength of the polariton changes, and we get yet different topological charges. Here we go from 1 to 3 to 5 charges based on the same principles I discussed before. This concludes my talk. I showed you a few examples of great opportunities that come from combining tailored nanostructures with suitable materials. In particular, when the material responses are strongly coupled to the light oscillations, from giant nonlinearities to opportunities for valleytronics and twisttronics to manipulate strongly nanoscale light and even carry information through these polaritons, to opportunities that come from low symmetry crystals. If there are any.
Terrific. And I'll warn Professor Alou and the audience, I'm having a little trouble with my internet freezing here, but Professor Dewan is ready to take over if necessary. Well, that was a terrific talk, and really appreciate catching up on your work. I had a question about the materials. Does one ever see effects on the materials from this, essentially focusing of fields? Are atoms moved around? Do you see kind of local effects in these, rather intense fields in those spots? And can one possibly use those to advantage as well?
Absolutely. This is actually a great question, very timely. For now, yes, we are exploiting some material changes in these structures. When we observe these nonlinearities, this is evidence of material responses that come from these large field concentrations. For instance, what I was showing in the first part on these intersub-band transitions, in which we move electrons from one level to another in these multiple quantum wells, is evidence of this. But this is just a very simple initial direction for what you are envisioning. In fact, at the moment, we have been looking into ways of facilitating chemical changes or strong material changes that come from these polaritonic phenomena. This is growing field, this polariton chemistry, for instance, in which we may be able to actually modify the chemistry through these fields, and at the same time exploit these changes to actually manipulate light. So there is a two-way connection here, and the field, in my opinion, has untapped opportunities that deserve a lot of investigation. It's a very exciting time in which we can control these nanostructures, and at the same time we have the opportunity of this very interesting phenomena happening at the material level.
Very interesting. Yeah, I think you have a wide open field here. It's indeed very exciting. Yeah. Well, let's thank Professor Alu again for this terrific talk, and congratulations again on the award. Again. And now it's my pleasure to bring up our third and final speaker of the session. Professor Jinan Bao is the KK Lee Professor of Chemical Engineering at Stanford University with additional appointments in chemistry and materials science. She's also the chair of chemical engineering there. She's a member of the National Academy of Engineering and the American Academy of Arts and Sciences, a fellow of the ACS, AAAS, and SPIE. She's won many prizes, including the L'Oreal UNESCO Award for Women in Science, the ACS Award in Applied Polymer Science, and the Willard Gibb Balby Medal, and the ACS Nano Award Lectureship. She also serves on our editorial advisory board and is a frequent author. She's renowned for her work on organic field effect transistors and semiconductors and their applications in flexible electronics. It's a great pleasure for me to introduce my friend and inspiration, Professor Jinan Bao. Jinan, the floor is yours.
Okay, thanks, Paul, so much for the kind introduction, and Professor Duan and others for the invitation. I'm also pleased to see several UCLA alumni and my former postdocs, Lei Fang and Alex Eisner, in this room. So great to see everybody. Okay, so let me go to my slides. Today I'm going to tell you about some of the recent progress on the skin-inspired electronics, which is an area we have been working on for quite a number of years. But I think now it's really getting to a stage where I think all the parts in place, and I think it's ready to make some difference. And I will start with motivation, some of the status of the materials development devices, and touch a little bit upon the potential applications, and then finally summary and the future outlook. As we all know, transistor has been the foundation for all the modern electronics, but transistor is made with silicon, and silicon being a rigid and brittle material, the electronics made with them are also rigid and brittle. If we use them to make electronics that are used to interface with human, they are also becoming similarly bulky and uncomfortable. And even for implantables, today's implantables are still based on very large, bulky devices. And here, of course, the battery is a major part that brings the rigidity. But nevertheless, still traditional materials and the electronics are being utilized. So what we envision is a future where electronics can truly integrate with human and provide comfortable, invisible, imperceptible, biocompatible, and autonomous monitoring and diagnosis to human. And skin has been an inspiration for my group for more than the past decade, but we were not the first realized actually many have been fascinated by skin for a long time, initially with the sensing capability for prosthetic hand, and then for touch screen, and also including science fictions. But it wasn't until I think really after the 2000s, Takao Sumiya's group in Japan really made a very important contribution in pointing out that organic electronics might be really suitable for mimicking the flexibility of skin and conformability of skin. And they didn't invent any new sensors, but they were able to really put together for the first time organic electronics and the sensors to show the possibility. And John Rogers' group is one of the pioneers who showed us the power of really taking advantage of the current already commercially available inorganic components and materials and make them flexible and even stretchable. So in my group, our path in this field really started from the initial fascination of the sense of touch, and as we thought that flexible electronics can potentially mimic the human skin sense of touch functionality. So we invented this or discovered that using pyramid structure can allow us to make very thin, flexible touch sensors that can, for the first time, show sensitivity that's comparable to human skin. And then I think the most important contribution we bring to the field is really on the one aspect is on the materials side. That is, as we started to mimic the sensing functionality using organic electronics, we started to realize that the skin, or starting to view skin as a material, that is not only flexible, but also stretchable, biodegradable, and self-healing all at the same time. So if we're able to mimic these materials property of human skin and incorporate into future electronic materials, we believe this can open up many new possibilities for the future of electronics. And the other important aspect that we realized while trying to understand how skin really sense information from external stimuli and communicate with the brain is that we learned that actually the skin through the mechanoreceptors actually converts the sensing signal into digital signal, basically this frequency signal. So essentially skin is doing signal pre-processing upfront, right at where the sensors are. And this allows signal to transmit over very long distance without adding, without compromising too much the signal quality, and allows long distance transmission and also neuromorphic computing. So essentially the skin, from the point of view of electronic system, it's also very advanced. It combines sensors and signal processing. And then after the pre-processing signal is all go to our brain, which is you can think about it as the microprocessor equivalent. So this is really our vision for artificial electronic skin. The possibility of the new materials will allow us to basically build the mechanoreceptor as artificial mechanoreceptors that does similar function, sensing, signal processing as human skin, and generate signal that can be directly interfaced with either biological system or as a way to reduce power for signal processing and also improve the quality of the signal. So that's really our vision for artificial electronic skin. And you may say that, well, silicon is already so advanced, you can integrate so much functionalities, including sensor, into this very little silicon chip. And indeed, that's the case. And in that case, you would have sensors, signal processing, and also I have a typo, signal conditioning and signal processing, all combined in this very little area. So that's perfect if you want to perform sensing in a very tiny region with extremely high density. However, if we think about the information from human body and also how our human body really operates based on the communication through the whole body, through electrical and the chemical information. And these information are generated at cell level, basically 20 micron or tens of micron or so, but they are interconnected or communicating over the whole body. That's in the order of meters. So then if we want to ultimately be able to have information for the whole body and be able to understand how these different information, when they are simultaneously being generated, how they impact our health and the behavior, then it requires us to be able to ultimately map all the signal from the whole body all at the same time. And it will be difficult to realize that by just having little chips, of course, implanted everywhere. And that's why having sensors distributed over a very large area, but at cellular resolution would be extremely important. And the other aspect is the signal pre-processing is really important because the power that's going to be needed to process all the data that comes from so many sensors is going to be enormous if we still use the current computing methods. But the nerve-like signal processing basically generates spikes. And the spikes are combined at these synaptic junctions. So the mechanoreceptors are these green dots representations. They can get stimulated by external force, vibration and so on, and generate these frequency pulses and get combined as synaptic junction. And if we take two devices that we use our stretchable electronics to generate the spike information, then combine into a synaptic transistor, then you can see, depending on the external stimuli, it will generate certain frequency pattern. And this could be learned to train the system to understand how this relate to certain size or shape of an object eventually. So this would potentially significantly reduce the power consumption as well. And furthermore, these new forms of electronics could also completely change how electronics are going to be like in the future. This is just an image that was depicted by Times Magazine. So we think to realize this vision, organic polymers are actually excellent candidate because they are already known to have good charge transport property, especially if ultimately we can take full advantage of intramolecular charge transport and overcome this hopping limitation, and have ways to really improve the interchain charge transport. Then their charge carrier mobility would be significantly improved. But even with the current development, the charge carrier mobility for organics are highlighted in pink here. The inorganics are shown above the red arrow. The organics are below. And for various organic-based materials already, charge carrier mobility on par with that of polysilicon, and on par with thin film carbon nanotubes and oxide are already have been reported. So in terms of electronic properties, they already have suitable electronic property that can be leveraged to add new functionalities. So the biggest challenge that we are facing is to really be able to add the new functionality. For example, stretchability is a big important requirement we need to be able to realize so that these electronics can accommodate the movement and changing size and shape of biological systems. And here the requirement for these materials, for these polymers, typically is disordered polymer and very flexible chains. But for charge transport, we want rigid polymer chains, fully conjugated, and have good pi-pi interaction, which inevitably will generate these rigid crystalline domains. So without really understanding how to design these polymers specifically, the existing polymers, even though they have high charge carrier mobility, they can crack very easily, even at a relatively small strain at less than 25%. So our challenge is really to understand how we can address this kind of conflicting molecular design requirement and really be able to come up with materials that can meet the requirements of both sides. So in order to do that, we spent a lot of time trying to understand what really is happening when we apply a force to a polymer system and that is able to transport charges. What happened in the molecular level and which will directly impact their mechanical property. So basically a number of molecular changes or rotation, elongation, chain elongation, alignment, crystal reorientation, crystal breakage, and eventually bond breakage. These are the basic processes that take place in these molecular thin films. And of course, if there are irreversible processes, then the film either become plastic and cannot return to its original shape, therefore not elastic, or if the bonds break, then cracks will form and the material will fail. So we need to the molecular design we come up with need to basically remove all the irreversible processes and allow everything to become reversible. Then we will have a material that can be repeatedly changing some of the, even though molecular scale conformation and alignment, but it can always return to its original arrangement. So I just show a few examples. The one molecular design example we come up with is to partially to reduce the rigidity of the conjugated polymer and reduce the large long-range orders, but promote short-range orders by incorporating just 5 to 10 molar% of non-conjugated units. But here, instead of just having any kind of simple LQ chains or other non-interacting non-conjugated unit, we found that adding something that can promote weak intermolecular interactions such as hydrogen bonding could allow additional energy dissipation mechanism to help adding another mechanism to allow these polymers to become more stretchable without decreasing the charge transport. And then another more general method that we have discovered initially was just thinking naively that you kind of mix the electronic conductive part with a stretchable component, you make a blend. Of course, you will have both properties, but of course, the expectation, actually my prediction when the students wanted to try it, I thought it's just going to significantly decrease the electronic property. But interestingly, we found that if we choose the right pair of polymer semiconductor and this elastomer matrix, it actually promotes, even in solution, but later on from thermodynamics point of view, it makes a lot of sense. But anyway, in solution, we already observed the aggregation of the conjugated polymer can form nanoaggregation, even promoted in solution as we add the insulating components. And furthermore, we discovered a phenomenon that hasn't been observed before for conjugated polymer, even though it was already known for polymers like polystyrene or PMMA. That is, when you make these nano-confined structures, the glass transition temperature of the nanostructure compared to thick or bulk polymer material, the glass transition temperature can decrease. And we observe this decrease can be as much as 80 Celsius compared to that of the thick film made of the same polymer. And this decrease implies that the polymer chain dynamics becomes increased, meaning the polymer becomes slightly more flexible and more mobile at room temperature. And this also allows these nanofibers to become more ductile and can be subject to stretching without causing cracks. And also it's accompanied by reduction in the overall crystallinity because of the confinement prevents large crystal growth. But the end result is not only we achieved a very robust elastic semiconductor, but rather unexpectedly the charge carrier mobility compared to the pure neat polymer semiconductor, but we add actually 70 weight% of insulating polymer into this blend, we actually see quite a large boost in charge carrier mobility. But of course, this boost in this particular case, we also added a little bit alignment of the fibers. But overall, we had several times enhancement of charge carrier mobility in this case. So with such approach, now we can take the stretchable semiconductor from initially this development started only kind of in the after 2010, more in the mid 2010. And at that time, the charge carrier mobility were really low because of the failure of due to cracks for stretchable semiconductors. Or just simple blending that cause reduction in the charge carrier mobility. But now our stretchable version can also have charge carrier mobility on par with those of the best polymer semiconductors out there. And this approach is very versatile, can be applicable for us to to incorporate other skin-like functionalities, again, without degrading the charge transport. For example, if we want biodegradability and elasticity at the same time, we designed a elastomer that's both biodegradable and elastic and compatible with our polymer semiconductor, which also has a labile conjugated unit, this imine unit, to allow it to also degrade, but it forms these beautiful nanostructures, which allows enhancement of charge transport as well as good stretchability and biodegradability. For self-healing, we can incorporate our semiconducting polymer together with a self-healing matrix, and again, being able to maintain the charge transport and add the new functionality. With our initial study, even though it still have a lot more work to do to fully understand the molecular level information in what's happening in all the different systems. However, we now already have a collection of materials, either conductors, semiconductors, and with the stretchability, self-healing, and the biodegradability, all incorporated into these materials. So the current type of devices we make, they are always supported onto stretchable substrates, and we can bend and fold them and twist them and even use sharp object and still be able to maintain stable current output. So with materials in hand, then the next step is really processing. So if we look at the development of transistor history, it started out with really very large transistors to show the concept. And then silicon was discovered to be the most suitable material. So that was a materials development. And then integrated circuit was shown by Texas Instrument. And then it wasn't until photolithography was developed that which is a processing method that's being used to produce all the transistors nowadays. And that allows transistors to continue to follow this Moore's law and shrink size continuously over time, and also improve the speed and the performance over time. So this is this processing is really a key enabler in addition to having the suitable material. And same thing with our case, because from material, we need to, again, pattern all the layers without damaging each other and without degrading the electronic property. And we need more than just one transistors. We need hundreds, thousands, or millions in order to do anything meaningful. So that's what we have been developing over the past few years. And the key guiding principle we have is that we want to be able to have a process that's high yield and reproducible, so that we can actually produce meaningful circuits. So that means we cannot have any transfer process in our case, which may slightly decrease the yield. But even with 99% yield, and if we have 60 transistors in a circuit, that means after all the fabrication steps, we only have 50% yield of the circuit. So we really need a 99.9% or 100% yield. So in our process, we first put a sacrificial layer that's water soluble, and then we develop a photopatternable dielectric and the process for semiconductor. So dielectric, semiconductor, and then we pattern the drain and the source, and then we cast a elastomer substrate, and then we immerse this into aqueous solution, which will lift off the material and together embedded into the elastomer. And finally, we can add the interconnects and the drain and the source electrodes to complete. So this just shows direct photo patterning using AZI chemistry for the dielectric layer. And then for the semiconductor, our first generation was rather complicated because the semiconductor itself was not photopatternable. So we have to add a first fluorinated a metal layer to protect the surface, and then a fluorinated sacrificial layer, and another metal layer for preventing the etching damage. And then we will pattern everything and etch the semiconductor, and then remove all these protecting layer. Inkjet printing can also be used, but then the uniformity was limited, so we still prefer the photo patterning method. In the end, we have to put down drain and source electrodes and gate electrode. Our first generation, we use a shadow mask and spring coating, and that limited our density to around 350 transistors per centimeter square. But nevertheless, it allows us to start building arrays of devices. This is a 10 by 10 transistor array, 100 transistors with 100 touch sensors for sensing objects. And also basic circuit blocks could start to be built, such as amplifiers, ring oscillators, and so on. These are all the basic building blocks. And but the first generation kind of basically step shown on the left took many steps, and the density was still limited. So we more recently developed a second generation where all the components, including the electrodes, were all photopatternable, so that we can significantly increase the density. For the conducting material, instead of the carbon nanotubes, here we developed a photopatterned conducting polymer process. And here the crosslinker is chosen so that this crosslinker actually induces some physical pi-pi stacking between the p dot. So the addition of this crosslinker actually improves the conductivity. But if we add too much, there's too much physical crosslinking, then the we won't be able to develop a photo. After photo exposure, we won't be able to remove this polymer anymore. But if we don't incorporate enough crosslinker, then there's also not sufficient difference with or without photo exposure. So with the right amount and the right PEG unit in the middle, then we are able to have a quite nice reproducible process that can pattern our drain source electrodes down to a few micron feature size, and with pretty good conductivity that's in the hundreds of Siemens per centimeter. For the semiconducting layer and dielectric layer, so semiconducting layer, previously we used metal mask and lithography and etching, but currently we have this new crosslinker that's based on diazyrine, which provides a mild crosslinking with the semiconducting layer without decreasing any of the electronic property. And this can also be used to pattern the dielectric layer. So with these new development, now we can reduce the size of the transistor. Here, these two images on the left and right are similar scale for the transistor array. So you can see we significantly reduce the size, and now the density of the array can increase to 42,000 transistors per centimeter square. And they're fairly uniform, and even with only part of the fabrication carry out in clean room, not all the processes were done in clean room. We were still able to realize more than 95% yield for the devices. Of course, they are stretchable and maintain the electrical performance, and this is what they look like. So when I give a talk last week, actually Professor Yang from UCLA was there. After the talk, he asked me, why do you need such a high density? Actually, for high density, one is for the speed of the electronics. It will depends on the feature size. And the other thing is with our ultimate vision of large area sensing, where we want to incorporate both the sensor and signal conditioning circuit together next to the sensor, then we will want these circuits to be small enough size so that we can still maintain the high resolution sensing that we can achieve with our sensors. So that's a very important consideration, to have high density transistors that we are able to fabricate. So for the transistor, they are the basic components. Now we're already at 42,000 per centimeter square. And the next generation, hopefully we can get to 100,000 per centimeter square, and also with a boost in charge carrier mobility. 13.5 megahertz diodes, they're important for wireless devices, and that we have it already demonstrated. Also stretchable polymer LED, that's demonstrated. Stretchable solar cell, stretchable lithium-ion battery, temperature and various sensors, and also neurotransmitter sensors is coming out, and also passive wireless sensor tags. So basically, these are all the core components for building any electronic systems. We're taking the initial steps, but I believe that with a little bit more time, that all the parts will come together, and we can really start to see systems that are truly skin-like. And these are just sensors, which I won't go into detail. And one point I want to really emphasize is that for these electronics, I think the true advantage is really interfacing with biological system, with their softness, the modulus match, with the biological system without causing scar tissue formation or tissue damage, accommodating movement of the biological system, and also allow accommodation of changing size of the growth of biological system. For example, if we have implantable electronics implanted when the person is young and then grow into adult, all the size of the person, of all the organ has increased in size. And if the electronics remain the same size, it could cause damage to the person, such as a nerve cuff used for implant to the child's vagus nerve. It will constrain the nerve and has to be surgically removed later. So having electronics that are ultra soft and doesn't constrain the growth could be very interesting. So that's an area I think it could be something quite unique to these systems. And the other true advantage, it was pointed out very early on by Dave Martin, that is this conducting polymer being also having some surface area. It has high capacitance at low frequency. So as a result, when conducting polymer is interfacing with tissue, it results in a low interface impedance. And this can be several orders of magnitude lower. And this implies that the signal to noise ratio we can obtain with these kinds of interface would be much higher signal to noise ratio. And that means we can have smaller size electrode and higher resolution and they really go to the cellular resolution. And also if we use them for electrical stimulation, the voltage required can be potentially lower. So then these are truly advantages on the performance side. And of course, then it can enable these mapping in the organ at cellular resolution, mapping of the muscle movement at cellular resolution, where if we use rigid devices, then they have to be interconnected by some stretchable wires, then the density will be limited by these having to incorporate these wires. So to summarize, here I've shown you the our vision for artificial electronic skin. That is not only the materials are incorporating the skin-like properties, but also these artificial skin are capable of sensing and signal conditioning, pre-processing, like our human skin. And this creates a new type of form of electronics that can potentially allow intimate interfacing with human body, and also can hopefully enable many new possibilities for other consumer electronics applications. So we do believe that skin-like sensor circuits and the batteries can potentially change our relationships with electronics and with each other. And we hope this can become part of us and part of our life. Finally, I'd like to thank my research group. This was a while ago when we were still able to all get together. But now again, I'm very excited about it, and many funding agencies and also seed funding from Stanford to seed many of the activities and collaboration with many groups from different areas. And thank you so much again for the invitation, and I'll be happy to answer any questions if there's time. Thank you.
Terrific. Thank you so much for the beautiful talk. Let's start with a question from the audience, which comes from Madhurima Deb, who says, hello, Professor Bao. I would like to know whether biocompatibility tests are needed for this kind of assembly.
Yeah, certainly. The both biocompatibility with on-skin devices, as well as, or especially for devices that are implantable. And currently, we only have tests for some of the materials for a few months. Implantation, and in most cases our device and those devices are with substrates that are already known for that's FDA approved for certain implantable applications, and but then there are embedded materials that may still not have been previously tested, and we are hoping that at least with a hybrid system, or maybe if the device are mostly encapsulated by approved materials, it may shorten the path for approval.
And then I had a question that's maybe partially philosophical. You and people in the field have done so much to improve the materials and their properties, and particularly conductance over time. But nature uses materials that are pretty lousy for conduction. And, I wonder if you have some thoughts on that, and what, if there may be some special properties there that are, that we haven't yet considered, or, if there's some exploration opportunity is maybe what I'm thinking in looking at how, how charge is effectively moved around in biological systems.
Yeah, Paul, that's a really great point. Yes, in nature, many of the electrical signal are transmitted or firing at only a few hertz for the stomach muscle, and then for brain wave, it will be up to kilohertz at most. And so they are, but our modern electronics go to gigahertz. So it's there's a huge difference in the frequency and also power consumption. And the neuromorphic signal processing, that's really a very important key difference between biological system and our computers nowadays. And this pre-signal processing using spike-based or spike-encoded information that's used by biological systems is really important. As you can imagine, many combinations of these spikes that are combined at a synaptic junction and generate a pattern of a certain frequency and amplitude that can correspond to a size or shape of the object. So instead of our computer scanning every single pixels and try to reconstruct the information, it already knows this pattern is that object. So there's much to learn for us from biological system, and that's why we felt that the place where we can make a difference and really differentiate from what the high density silicon devices can do is to go to these kind of sensing systems where you have all the processing right next to the sensor. And for the whole body sensing, the resolution is tens of microns. So there's plenty of real estate for us to utilize with even just our current standard photolithography.
Terrific. Well, that was another amazing talk, and let us thank Professor Bao and all the speakers from this morning. I'll turn things back over to Professor Duan, who maybe will let us know what's coming up in the rest of the day.
Okay, so actually, this pretty much concludes our session. Actually, before we end, actually, I still want to ask Professor Bao a question.
Okay, you got to flip one more in there.
Yeah, it's a beautiful talk. So it's amazing to see this stretchable polymers. They can be so stretchable, will get even better electronic properties. So I'm curious for many of the devices we're making now this way, even the material making them better and better and more and more stretchable. We very often still place them on top of substrate. So I'm curious whether the substrate would be a issue for future applications, particularly if we want to interface them with biologic, for example, biologic system, particularly if we go to even onto cellular scale, substrate itself may pose some additional rigidity. Even though it's stretchable, if you have a finite thickness of substrate, there's always going to be an issue for the conformability or something like that. I'm wondering whether that is an issue or not.
Well, so far, seems the substrate has not been a limiting factor for the stretchable substrate. For example, SEBS, it's has very high toughness, and we can go down to submicron thickness, and without and you can stretch it without breaking it easily. And also, they can be designed even if you use a needle to poke it, the crack will not propagate. So then those robust substrate can really allow us to go to very thin substrate. And also there are development in the polymer field where instead of a conventional kind of thin polymer chain, if you use polymer brushes, they reduce the entanglement. Then the modulus can go down from the typical elastomer is megapascal, can go down to kilopascal. So then that's really, really soft. And also at the same time, if it's micron thickness, then it will feel like nothing when you put it against the skin.
Yeah, sure. One more related question. Would the permeability or breathability be a factor to consider for this type of application?
Yeah, I think definitely the for that that will be something to be engineered into the device. Maybe have certain porous structure allows the breathability. Yeah, so that would be an interesting potential combination of, because I see some moth cough talks here, then those are potentially interesting structures that provide control the porosity maybe.
Okay, thanks a lot. Thanks a lot. So I guess that really concludes our session today, and we would really like to thank all our speakers, and certainly congratulations to all our awardees, and thank you all, and thank you, Paul, for spending the entire morning here. And we are going to have another keynote session tomorrow, and so we look forward to see at least some of you here again. And thank you all.
Thank you.
Bye.
Thank you. Thank you, everyone.